Welcome to the AWS Certified Solutions Architect Associate Complete Video course. This course was developed specifically for the latest edition of the exam released in February of 2018. The AWS Solutions Architect Associate certification is ideal for anyone in a solutions architect or similar technical role. This certification demonstrates that you have the ability to gather requirements and design an effective solution using architectural principles and best practices, and to provide implementation guidance throughout the life cycle of any project. This course is designed to help you pass the AWS Certified Solutions Architect Associate exam. We will cover all the key areas addressed in the exam and review a number of use cases designed to help you ingrain the principles and practices on which this certification is based, so that you have a framework with which to formulate the correct answers. Throughout this course, you will gain a deeper understanding of AWS architecture following the 5 pillars of the well-architected framework. Just a little about myself and my background. With a long history of web and mobile application development, I started using Amazon Web Services in early 2009. The first project I deployed to AWS went on to receive nearly $1 million in seed funding, and that experience convinced me that AWS was the future of my career. Over the last 8 years, Amazon Web Services has added a myriad of new services and features, and I have worked constantly to deepen my knowledge of and experience with their offerings. I've worked with companies of all sizes to both migrate workloads to AWS and build cloud-native applications. As of this video, I have 7 AWS certifications, including the Solutions Architect and DevOps Engineer professional levels and the Advanced Networking Specialty certification. I am also the author of several AWS-related videos published by Pearson. The AWS Solutions Architect Associate certification is perhaps one of the most valuable certifications an IT professional can currently have, but achieving it requires studying a number of key resources and the ingraining of a significant body of knowledge. This module is the first step on your journey to becoming an AWS Certified Solutions Architect. To pass the Solutions Architect Associate exam, there are a number of key, useful resources and materials to study. In this lesson, we will review preparation resources, the exam guide, registering for and taking the exam, test-taking strategy, and more. Now let's review the Solutions Architect Associate certification. So this course is specifically designed for the new exam that was released in February 2018. It is worth noting that there is an older version of the exam that should be available until August of 2018. But again, this course is specifically meant for the newer version, released in February of 2018. So when you go to register for the exam, be sure that you are choosing the new version. Right? And this certification is intended for solutions architects or those of us who may be in a similar technical role. Now, it does demonstrate, this certification demonstrates your ability to effectively gather requirements for a project, to your ability to use architectural design principles to define solutions for those challenges, and to provide implementation guidance to your team throughout the life cycle of that project. Now, it does assume that you will have somewhere around 1 year of hands-on experience using AWS technologies, including compute technologies such as EC2, Lambda, the Elastic Container Service, networking technology such as VPC, including all of the things that go along with VPC, such as routing and firewalls and other types of controls and configurations. The exam will also test your knowledge and experience with storage technologies such as Amazon S3 or EBS, right? Object and block storage, file storage with EFS, and so on. Databases as well, such as RDS, DynamoDB, Redshift. You will also need to demonstrate your knowledge and understanding of AWS best practices, and we will review those here in an upcoming lesson. There is a white paper that outlines 10 best practices, and you will need to be familiar with those. You will also need to be familiar with the AWS global infrastructure, such as regions, availability zones, edge locations. You'll need to be very familiar with why and how we use such things. Again, networking technologies within AWS, how to configure secure networks, and remember that for applications that run on EC2, the network underlies that infrastructure. So you really need to be very familiar with how a network can be configured to provide not only security, but also high availability and or performance. Right? There are also a number of security features throughout AWS within our identity systems, within our network, within our applications, and with our configuration of managed services. And you'll need to be very familiar with that as well. And one last note I'd like to leave you with for this lesson is that as you move forward in this course, and after this course, as you move forward to continue studying and preparing for this certification, what I would encourage you to do is study with the intention of becoming a good and valuable solutions architect. Study for the intention of being effective in your career. Study with the intention of being a valuable member of a team and bringing, expertise and knowledge and experience of AWS to that team, rather than simply studying in order to pass an exam, right? So by studying to really truly ingrain this material so that you can be an effective solutions architect, you'll naturally pass the exam. Now let's review exam preparation resources. Now, there are a number of resources available to us from AWS to help us prepare and study for the Solutions Architect Associate exam. We should start with the exam guide, and we will talk more about that here in an upcoming lesson. We also have sample questions. We have a practice exam available to us, and there are a series of white papers that would be really good for us to read and study. Those being Architecting for the Cloud, AWS Best Practices, and the Well-Architected Framework. You can find information about all of these resources here at the following URL. Now, the exam guide is available online as a PDF. It will outline recommended knowledge that you will need in order to pass the Solutions Architect Associate exam. It will also outline the white papers that we've talked about that are helpful for studying. It will also describe the scoring model and how you can expect to be scored on the exam, and it will list the domains of the exam, those areas of study that you need to be familiar with in order to pass the certification. Now, it happens, as we'll see here in just a little bit in an upcoming lesson, it happens to be that the domains of the exam align one-to-one with the pillars of the well-architected framework. So the well-architected framework is going to be one of your best pieces of study material. As far as sample questions go, again, those are also available online as a PDF. They will offer somewhere around 10 questions. Amazon could change that at any time and offer more or less, but generally around 10 questions. The PDF will contain the right answers so that you can compare your answers with what AWS says is right. We also have a practice exam, which is definitely a good thing to try out. So practice exam does require registration. You register for it just like you would the real exam. It does cost approximately $20 US. Of course, AWS could change that at any time, but as of the time of this video, it is currently $20 US. Now, when you take the practice exam, it does offer an immediate pass or fail result. So you'll know immediately whether you passed or failed. And of course, you can take that practice exam online from home. You don't have to go anywhere in order to take it. Now, the thing to keep in mind about the practice exam is that it's just like the real exam in that it does not reveal any answers that you got incorrect. That will be up to you to determine based on how you felt about those answers. And so the practice exam is really helpful in helping you determine whether or not you are ready to take the real exam. And so what I've done for myself over the years, having passed 8 exams so far, is that for any exam that I wonder about, am I ready? If I took the practice exam and struggled with it, then that showed me that I wasn't quite ready for the real exam. But if you take the practice exam and you move through it with confidence and you feel good about it, then that would probably indicate that you're ready to go and pass the certification. Okay, so those are our preparation resources. Again, we have the practice exam, sample questions, the exam guide, and those list of white papers. And of course, some of these things we will take a closer look at in upcoming lessons. Now let's review the exam guide. So here we are at the AWS Certified Solutions Architect Associate webpage, available on the aws.amazon.com website. So just as a reminder, I want to point out that this course is designed for the new exam that was released in February of 2018. So that is the one that we are going to be looking at. So if we scroll down here, again, here are all of the key prep resources, and here is the exam guide. So let's go ahead and take a look at that. It does open up as a PDF. I'll bump the font size here a little bit. And so, again, the exam guide tells us all of the things we need to know about the exam in terms of what we should study, what we should know, and how the exam is going to be scored. So you can see here it does say that it will validate your ability to define a solution using architectural design principles, and we are going to talk about a number of those throughout this course. And then, of course, you will also need to be able to provide implementation guidance. So you, as a solutions architect, and you will have to rely on your knowledge of these principles in order to help your teammates actually implement, the choices that you've helped design. Now, in terms of recommended knowledge, you'll see here that we do need knowledge of a number of things, right? It does suggest 1 year of hands-on experience, and of course, that's up to you. Some of us may be able to gain this experience and knowledge and really ingrain this more quickly. So for some of us, that might mean 6 months. For some of us, it might mean longer, but generally somewhere around 1 year of hands-on experience. And you'll hear me say this again later in the course, that nothing beats hands-on experience. So by all means, practice the labs, actually design something and go and implement it. Even if you implement it, run it for a day and tear it down, that's okay. They also recommend, hands-on experience using a number of different services: compute, networking, storage, databases, hands-on experience with deployment and management services like CloudFormation, Code Pipeline, Code Deploy, Code Build, perhaps even things like Elastic Beanstalk or OpsWorks. We will need to be able to identify and define technical requirements. So part of the exam, a big part of the exam, the general pattern that you'll see is that questions will present a particular scenario. They will present a technical challenge saying, this is what is needed. This is what we're trying to achieve. Which of these answers will solve that, in the most reliable way? Which of these answers will give you the highest degree of availability, or the best performance, or the lowest cost, or the best security, right? You will need to have knowledge of recommended best practices. Of course, we will talk about a number of best practices in this course, and we will try to illustrate those with diagrams and discussions as we move forward. We will need an understanding of the AWS global infrastructure. You will need to be very familiar and just off the top of your head know exactly what we mean. You know, when we talk about regions, availability zones, and edge locations, you will need to know which services, you know, what scope applies to each service. Some services are global, some are scoped to a region, some services are specific to an availability zone. And of course, that knowledge will then help you determine whether or not a particular solution would help you achieve high availability or performance or cost savings. We will need to have an understanding of network technology, so you do need to know Amazon VPC pretty well. We'll need to also understand a number of security features and tools, right? Amazon KMS for encrypting data at rest, options for SSL in terms of encrypting data in transit. We will need to know different tools around monitoring and logging, tools within our network such as firewalls for the subnet, firewalls for instances, things like that. Now, in terms of exam preparation, you can see here that the exam guide is recommending these white papers, the best practices and the well-architected framework. And of course, this course is designed, the rest of this course, the following modules are designed directly from the well-architected framework. So what I would recommend is that as you watch the rest of the course, I would also read the well-architected framework and correlate what you're reading in those white papers with what you're seeing and hearing in this course. And that will really help ingrain this knowledge. The exam itself, multiple choice and multiple response. So multiple choice says, you know, it will have one correct response and you will choose that one correct response out of 3 or 4 possible responses. Multiple response will typically say, out of these 3 or 4 choices, choose the 2 that provide the correct answer. Now, again, it's worth noting that if you go through the exam in terms of unscored content, your exam may include items that are placed on the test to gather statistical information. So you may end up answering a question or two or more that is not actually being scored. AWS is putting those questions in there just to try to evaluate the general body of knowledge that is out there among, you know, takers of the exam. In terms of the exam results, it is, as it says here, a pass or a fail, and then your results are reported as a score from 100 to 1,000 with a minimum passing score of 720. So you don't need to pass, even though if we go down here toward the bottom and you see these domains, and you'll see that these domains have a particular percentage of the exam, we don't have to necessarily be so concerned about passing any one domain over the other. It's just an overall score, right? And so you'll see here that these 5 domains, resilient architectures, performant architectures, secure applications and architectures, cost optimized and operationally efficient or operationally excellent architectures, those 5 domains align exactly with the 5 pillars of the well-architected framework, and they align with the remaining modules in this course. Right? So again, I would highly recommend so that you are prepared, so that you know the things that you need to continue to study, the things that you want to really absorb and ingrain from this video series. I would encourage you to go through and read the rest of the exam guide, and that will help you be much more prepared for actually taking the exam. Now let's review registering for the exam. So here we are at the AWS Certified Solutions Architect Associate webpage, available on the aws.amazon.com website. From here, to register for the exam, we're just going to click here, Schedule Your Exam. And that will open a new tab bringing us to the AWS Training and Certification portal. From there, we need to sign in to our certification account. So if you don't already have one, you can go ahead and register for a certification account. So we'll go ahead and click there. And then here it says we can sign in with an existing Amazon account or create a new one. So our AWS training and certification account is intrinsically related to our Amazon account. We don't have to use the current Amazon.com account, that we use for personal shopping. We can always create a new one specifically for AWS. So I'm going to go ahead and click sign in, and from here we will go ahead and let me get my password. So we'll go ahead and I'm going to choose that, fill in my password, and log in here. Now that we're logged in, you can see that the certification account, we can scroll down, and if you've taken other exams like Cloud Practitioner or anything else, you would see the recent activity there. And of course, you can go over to Achieved Certifications and see any other certifications that you might have achieved already. If this is your first exam, your first certification, once you achieve it, you will see it listed here. And you will be able to download the logos and apply those to your email signatures or business cards or whatever. And so here, we'll go to Home, and then from there we will click Schedule a New Exam. Now this will then take us to, you'll notice that the URL changed. We are now in aws.psiexams.com. The actual exam is managed and proctored by a third party called PSI. PSI runs the actual training center locations where we go to take the exam. And so you can see here that I have a number of exams that are ready for scheduling. A couple of recertification exams, and if we keep scrolling down here, now what I want to draw your attention to is this one here. You'll notice it says Certified Solutions Architect Associate. That is the old exam. And again, this course is for the new exam released in February of 2018. So what we want to look for is, as we scroll down here, what we want to look for is here it is. Here's the practice exam, the Certified Solutions Architect Associate practice exam released February of 2018. So if you want to take the practice exam, which I highly recommend, you could register for that one there. And you can, once you pay for it, you can then go and immediately take that exam online from the comfort of your own home or office. You don't have to go anywhere in order to take the practice exam. So again, keep that in mind, that what you're looking for is that note saying released February of 2018. We are also, let's see here, I do believe you'll see that I actually took this exam a while back, the Certified Solutions Architect Associate released February 2018. So because I've already completed that exam, I don't have the ability right now to reschedule that, right? So for the sake of showing you how to register for an exam, I'm just going to choose another one, right? But of course, you would choose this one here, Certified Solutions Architect Associate released February 2018, right? So let me just choose another one real quick, just to show you how we register for an exam. So one that I actually need to schedule is the professional recertification. That one, my professional is expiring soon, so I need to recertify on that. So we can do that by scheduling the exam. Yes, you will verify that you are registering for the Solutions Architect Associate February 2018. And then we will select a language. The Associate is only available in English right now as of the time of this video. We will then find a location. I'm filming these videos, I'm in San Francisco at the moment, but normally I live near Denver. So I'm going to find, let me just do a quick search here for Denver. So you will search in your location, right? Where do you want to take the exam? It looks like I have a number of options near Denver. So I could choose, let's say number 2, whatever location makes the most sense for you in terms of schedule and convenience. And of course, we can get a list view of those locations here. And then once we choose one, this one is at a local community college, then I can see these are the available dates. So I could go, well, maybe, you know what, I'm not going to be able to do it on the 30th, but maybe, let's see, maybe I can do it on June 8th. Once we choose the day, then we can choose the time. You know what, I probably can't make it there by 9:30, so let's choose the 1:30 p.m. And then from there, let's go ahead and continue, right? And then yes, I verified that's what I want to do. It created a booking, and now I would have to pay for that exam. So the associate exams are $150, right? So again, I'm only using this one as an example of how to register, but when you go through this, you will see that the fee for the Certified Solutions Architect Associate will be $150 US. If you have a discount or a voucher that you got from somewhere, you can enter that there, enter your credit card information, and then once you pay for that, then you are officially scheduled to take the exam. And remember that when you actually show up in person to take the exam, you will need to show proof of registration. So be sure that you get those emails showing that you did indeed register and pay for the exam. So that's how we can register for the AWS Certified Solutions Architect Associate exam released in February 2018. Now let's review taking the exam. So the exam itself is a multiple choice and answer type of exam. Multiple choice meaning that you essentially get to choose one answer from a list of possible answers, and multiple answer meaning that you oftentimes will be instructed to choose, say, 2 or 3 of the possible answers. And of course, to get it right would mean that you select the appropriate 2 or 3 that are intended to be correct. There are 65 questions on the exam. You will have 130 minutes to answer those questions, and you do have the ability to review those. Now, there is a practice exam, as we've talked about, that is $20 to register and take that practice exam. And then, of course, the exam itself, the real certification exam, is $150 US for the associate. Now, currently, as of the time of this video, the exam is available in English only, and that's simply because this is a fairly new exam. But as time goes on, I expect that AWS will make that exam available in other languages. Now, when you arrive at the testing center, you will need to bring 2 forms of ID, driver's license, passport, credit card, what have you. You will also need to bring proof of registration as well. Now keep in mind that in terms of cancellations or rescheduling, that up to 48 hours before the exam, you can cancel or reschedule with no fee. Less than 48 hours, there will be a $60 charge to either cancel or reschedule. But keep in mind that within 24 hours of the exam, you cannot cancel or reschedule. At that point, it's too late, right? So if you do miss the exam, then keep in mind that the fee is non-refundable and it does not count as failed. It just means that you missed it and you forego, the $150. Now, again, once you are at the testing center, you will leave your belongings in a locker. Your jacket, your car keys, your smartphone, your laptop, your backpack, everything you will leave in a locker. The exam testing software requires a password to get out of and a special key combination in order to leave it. So you really don't have the ability to leave the exam itself to go and research your answers. And so what that means is that all of the knowledge that you need really does need to be ingrained in you and available from your own memory and experience. Now you do have the ability to ask for scratch paper and pencils or pens so that you can diagram things or draw something out while you take the exam, but keep in mind that you cannot take those things with you. Amazon doesn't want you to be able to, write down the questions or answers and then take it with you and give it, to someone else. Now let's review a test-taking strategy. So when you're actually taking the exam, what I recommend, and I've used this to pass a number of exams, at least 8 so far, is to take the exam in 3 passes. So on the first pass, what I recommend is to choose what you know. Go with the answer that you feel confident about. And if you can't feel confident in, say, 5 seconds or so, if you find yourself sort of going, well, it could be that, then just move on. Mark that question for review and move on to the next question. So again, the first pass is moving through with confidence, choosing the ones that you feel really good about. And then, of course, you do get the ability to review. You can always go back before you submit the exam. You can always go back to the beginning and review the questions that you marked, or just go through it again. Right? So on the second pass, then we use the process of elimination. And we start by looking at the available answers. And then we choose the ones that we know are impossible or are just not right. Right? So they could be worded in a way that tells you, well, you know what, maybe Amazon S3 doesn't work that way. Or VPC, that's not possible with VPC. I might not know which one is right, but I do know that that one is wrong. And so by using the process of elimination, that narrows narrows the choices down to the ones that could be correct. And then on that third pass, just review. Go through and make sure if there's any questions that you've marked that you want to spend more time on. Now that we've gone through the exam twice, now we have more time to spend on those few questions. And so what we're trying to avoid is spending a lot of time on questions up front during the first pass. Because remember that if you leave questions unanswered, those will be counted as wrong. And so we want to save that time. We want to get through the exam answering as many as possible, and then whatever time is left, now we can feel good about using that time for those few questions that you might not feel as good about. Right? So by all means, on that third pass, review, and make sure that you feel good about your answer. Even if you're still not sure that maybe there's 1 or 2 questions and you're still not sure that the answer is 100% right, you should feel good that you've done your absolute best, that you've really tried to answer that question, and if you still can't, then at least you've done your best. And then, of course, after you've gone through those 3 passes and you get to that place where it says, yes, I'm finished, submit the exam, you have 130 minutes, right? Don't be in a race. Don't be in a hurry. Take your time. Use, the full 130 minutes if you need to. Once you've gone through those 3 passes and you get to that place where it says, yes, I'm ready, I'm done, submit the exam, then only do that when you feel confident that you've done everything you can to answer the questions to the best of your ability. Now let's review best practices within AWS. The AWS Best Practices white paper is available as a PDF at the following URL. And I would highly recommend that you read through this white paper in your studying for the certification. I would recommend that you read through this at least twice. But we can summarize those best practices here. First, enable scalability. Scalability gives you the ability to meet demand when you have it. Whether that demand is more web requests, more API requests, or more batch processing that needs to be done. Maybe that demand is more videos that need to be transcoded. Whatever it is, as the demand rises, we need our system to scale along with that demand. If our system can't scale and yet the demand continues to rise, then at some point we may be unavailable. And that scalability also applies not just to compute, but also to storage. As our storage requirements grow, so too should our storage planes, right? So we should enable scalability there. Some services, like S3, for example, just scale automatically, but other services like EBS may need to be re-provisioned in order to grow that storage. Think of EC2 and other resources as being disposable. And so when we think of that, that gives rise to a level of flexibility and agility that we didn't have before. Because now we're not trying to treat these servers as pets. We're not trying to keep any one resource alive, but instead we flip that paradigm over and we treat these resources as disposable. That gives us the ability to simply throw them away when we no longer need them. That gives us the ability to stand up an environment, run our tests, perform our experiment or test our prototype, get our results, and then throw that environment away and stop spending money on it. Instead of working really hard to get any one machine back into a usable state, we simply throw it away and allow automated processes to bring a new machine up into a known and working state. We should also leverage automation. And I've said this before. If you've watched any other material from me, you've probably heard me say this over and over again, that the only way to truly realize all of the benefits, the cost savings, the agility, the flexibility, the efficiency, the lower time to market, the list goes on. The only way to truly realize all of those benefits is to leverage automation. And we'll talk much more about that as the course goes on. Another practice is to leverage loose coupling. So instead of having multiple components that are tightly coupled, that are inherently aware of each other and depend on each other, such a thing can cause cascading failures. So we can help avoid cascading failures by leveraging loose coupling, by leveraging queues or load balancers between different tiers, so that any one component doesn't necessarily have a direct and intrinsic, relationship on something else. And that way, loose coupling says that, one component can continue to do its job while another component suffers a failure. Another best practice is to leverage services, not servers. The idea here is that we want our team to focus on building, adding the differentiated value to our applications rather than being burdened by managing the underlying infrastructure. And so the more that we can leverage managed services rather than, managing servers, the more that we can offload those operational burdens. We should also look to choose the right database for the right problem or for any particular scenario, right? There's always room for relational data. There will oftentimes be room for non-relational data. There's a time and a place to use in-memory caching or an in-memory database, and a time and a place to use a data warehouse. And so instead of thinking, well, I'm going to use relational data for everything or NoSQL for everything, really look and investigate the particular scenario and see which database technology actually makes the most sense. And then in that regard, look to see how that database can be used most effectively within AWS. Another best practice that helps our availability is to avoid single points of failure. Single points of failure will oftentimes lead to downtime, right? If that one thing fails, we have no built-in fault tolerance. That means that our time to recover will be longer. And then, of course, we want to optimize for cost. Now, cost savings is not necessarily the number one driver of AWS adoption, but of course it's up there. That's one of the primary reasons that we want to, that a number of organizations are moving to AWS, is to save money versus on-premises. But of course that requires using AWS in a particular way. we have to look for ways to save money. Another best practice is to leverage caching. We can cache certain types of data in a number of different areas. There are opportunities to cache things within memory so that we can get result sets much faster. There are opportunities to cache certain types of data, both static and dynamic content, at an edge location closest to the end user. But either way, leveraging caching can be a way of improving the performance for our in the experience for our end users. And then we want to apply security in layers. We have security in a number of different places within AWS. We have security within our account and the protection of our credentials. We have the security of our network, and then in the way that we configure firewalls for that network. We have security within our data, ensuring that data is encrypted in transit and at rest, and a number of options in regards to how we go about that. And then, of course, there's the security of our operating systems and security of our applications themselves. And so we should be looking at applying all of the right tools for all of those different layers. Now let's review the well-architected framework. Now, the rest of this material for this course is based on the well-architected framework, which is a collection of white papers. Now, this forms the essential foundation of knowledge that you will need to not only pass the exam, but ultimately be an effective and valuable solutions architect. Now, the well-architected framework is essentially a collection of best practices and processes, techniques, and concepts that have been gathered over the years from a number of different Amazon clients, not just AWS themselves, but other large companies such as Netflix and so on, providing best practices on how they achieve or how they solve certain technical challenges. And so the well-architected framework is presented in 5 pillars. We have the reliability pillar, which talks about availability and building systems that are reliable and resilient. We have the performance efficiency pillar, which talks about the efficient use of computing and storage and tools and services within AWS. We have the security pillar, which talks about keeping our applications, our network, and our data secure. There's the cost optimization pillar that guides us into making decisions in how to save money. And then lastly, we have the operational excellence pillar. And the operational excellence is really about the processes and methods and practices that our business uses to deploy and manage AWS services. And so again, as we move forward in this course, the rest of the material is based directly from these 5 pillars of the well-architected framework. You'll also notice that if we go back and look at the exam guide, that the domains of knowledge within the exam guide, there are 5 domains that align. Each domain aligns directly to one of the 5 pillars of the well-architected framework. So I would highly encourage you to not only watch this video series, but as you do so, read the well-architected framework. As we look to the reliability module of this course, read the reliability pillar of the well-architected framework. As we look to the security module or the cost optimization modules in this course, look to those pillars in the well-architected framework and correlate what you're reading with what you're viewing in this video. And I think that that will be a very effective way to go about studying for the exam. Now, of course, you can find the well-architected framework here at the following URL. Now let's talk about hands-on experience. You'll probably hear me say this again, but nothing beats hands-on experience. It is the greatest teacher we can have. And so the greatest thing that you can do to study for the AWS Solutions Architect Associate exam is to practice, to get into AWS and actually get your hands dirty, roll your sleeves up, get in there and build things. And one of the best places we can do that is to leverage or make use of the AWS labs. We can find labs available here at the following URL, aws.amazon.com/training/self-paced labs. And so let's take a look at that web page. You'll see here that we have a number of different labs. If we scroll down here, some of the recommended labs, I want to point out some that I think would be really helpful on your journey to studying for the Solutions Architect Associate exam. So if we take a look at the introductory labs, this will take us to amazon.quicklabs.com. QuickLabs is the company responsible for actually performing the labs. Amazon generally designs and implements the details of the labs. QuickLabs is, sort of the platform for running the lab environment. Some of the labs that I think would be really helpful, and of course, remember, you can always pause the video and take a note of these. Introduction to Amazon Elastic Block Store. For those of us who don't already have a significant amount of experience with these, then I highly, highly recommend going through and performing these labs. Introduction to Amazon Elastic Block Store. Introduction to Elastic Load Balancing. Introduction to Amazon Simple Storage Service. Introductions to Amazon Relational Database Service, either Windows or Linux, depending on your flavor of operating system. Introduction to AWS CloudFormation, Amazon Elasticache, Amazon Virtual Private Cloud, Amazon CloudFront, Introduction to AWS Identity and Access Management, Introduction to AWS Lambda, Introduction to Amazon Elastic Container Service, DynamoDB, Autoscaling, Route 53. And I think those would be a really, really good place to start. Those that I just outlined would give you a really solid foundation. And then, of course, any other lab that seems interesting to you would be helpful as well. The more that you can do, the better. But I think that those that I just listed would give you the best foundation to help you ingrain and understand, the services and the topics that we will continue to talk about throughout this course. Now let's review some key services to study. Now, I've organized this list according to the 5 pillars of the well-architected framework and according to the remaining modules in this course. Now, you'll notice that some of these services do repeat, and that's because they apply across various disciplines within, our use of AWS. So we have Amazon Virtual Private Cloud, or VPC, giving us the ability to create isolated networks. And of course, those networks then allow us to use multiple availability zones, giving us, giving rise to the resilience to the loss of a data center. We have AWS Direct Connect, giving us the ability to connect on premises to AWS in a high-speed private fiber connection. We have Amazon Elastic Compute Cloud, or EC2, giving us on-demand virtual machines called instances. We have Amazon Route 53, which is Amazon's globally distributed, very reliable DNS service, allowing us to perform a number of different types of DNS routing, including failover, so that we can fail over from an endpoint that is failing to an endpoint that is working. We have Elastic Load Balancing, Amazon CloudWatch, which monitors our systems and reports, any kind of an issues that might affect reliability. And then we have Amazon Simple Storage Service, or S3, allowing a central place that we can store a myriad types of data, logs, static assets, you name it. So these services, when used together in the right ways, can help us build reliable applications. We will talk more about that in an upcoming module. And then lastly, we have Amazon Glacier, giving us the ability to archive data for long-term storage in case we ever need to restore it for whatever reason. And so again, this group of services used correctly can help us build reliable systems. And we'll talk more about these services in that related module. For performance, we have auto-scaling, helping us to match the supply of resources with the current demand. We have Amazon Elastic Block Store, allowing us to create highly performant storage volumes. We have Amazon Elastic File System. Amazon VPC, our networks also underlie the performance of our applications. We have Amazon Elastic Container Service, or ECS, which allows us to more effectively utilize the resources in our virtual machines. We have Amazon CloudWatch that provides monitoring so we are aware of the performance of our infrastructures. And then we have the Amazon Relational Database Service, allowing us to offload the management of databases to AWS. And then, of course, we also have a high-performing NoSQL data store with Amazon DynamoDB. And these services, when used together, can help create performant applications. And again, we will talk more about those in the related module. For security, we have the Identity and Access Management Service, allowing us to create and manage users and credentials. We have the AWS Security Token Service, which creates temporary credentials. We have IAM instance profiles and roles, which allow us to delegate permissions to EC2 instances. We have AWS Organizations, which allows us to create and manage multiple accounts so that we can isolate our resources according to, different business unit, department, environment, and so on. We have AWS Config, which maintains a constantly evaluating our environment and comparing the state of our environment against rules that we specify so that we can be informed of any unauthorized or unexpected changes to our environment. We have Amazon CloudWatch Logs, which our applications and systems can send logs to, and it gives us a central place in order to collect those logs, and from there we can do a number of other automated processes to help create a more monitored and secure environment. We also have Amazon Elasticsearch Service, which can very easily work hand in hand with Amazon CloudWatch Logs to give us a more powerful way of visualizing, searching, and analyzing logs. And then lastly, we have Amazon VPC security groups, along with network access control lists and other mechanisms that we can use to create secure networks for our applications running in AWS. And then we also have Amazon Key Management Service, or KMS, which allows us to encrypt our data at rest. And this group of services and more we will talk about in the related module. For cost optimization, we have, again, Amazon CloudWatch helping us to monitor our infrastructure as well as our current estimated charges so that we can be aware of our current costs. We have the AWS Trusted Advisor, which performs regular checks of our environment and suggests ways that we can improve a number of things: reliability, performance, security, and cost optimization. We have reserved instances and spot instances as ways of saving money versus other billing models. We have AWS CloudFormation, which can help us create temporary environments and then tear those temporary environments down. That way we're only paying for a collection of resources when we actually need it. We have the AWS Cost Explorer, which helps us actually take a visual graphical look at our costs and helping us to understand where we're spending money within AWS. And then, of course, we have billing alerts. We have the ability to create alarms based on the amount of money that we're currently spending. Right? So this collection of services and features, when used in the right ways, can help us optimize for cost and save money during our implementation and use of Amazon services. And we will talk about those more in depth in the related module. And finally, we have operational excellence. We have a number of services, again, AWS CloudFormation, helping us to automate the creation and management of AWS services. We have AWS Code Commit, which is private Git repositories. We have AWS Code Pipeline, which can work hand in hand with Code Commit and CloudFormation to further automate everything that we do within AWS. We have AWS Lambda, which we can use to offload the operational burdens of running compute power. So that way our teams can focus on writing code and allow AWS to handle all that's necessary for the deployment and running of that code. We have AWS Config, like we mentioned earlier, can also help us stay on top of and be aware of changes in our environment and ensure that our environment remains in a good working state. We have Amazon CloudWatch, again, providing monitoring, and Amazon CloudWatch logs, allowing us to collect everything. So between the two, Amazon CloudWatch and CloudWatch logs, we have the ability to create an environment in which nothing goes unnoticed. And so a key component of operational excellence that we will talk about later is being aware, being educated, continuous monitoring, continuous reevaluation of our choices, and leveraging automation in order to make all of that happen. And then we also have Amazon Simple Notification Service, allowing us to send notifications about happenings in our environment, allowing us to be informed in near real time as things change, as incidents arise, and so on. And then lastly, we have Amazon Athena, which allows us to, let's say, for example, we're collecting Amazon CloudWatch logs that we have, a massive amount of log data that's then being stored in Amazon S3. We can use Amazon Athena to query those logs and derive value and meaning from those as well. So when we look at this long list of services, it might seem daunting at first, but over time, you will gain a familiarity and then a more in-depth understanding of these services as you continue to study and as you continue to gain some hands-on experience with these services. Now, keep in mind for the Certified Solutions Architect Associate exam, you don't have to be an absolute expert in every service. You don't have to memorize every little detail of all of these services. The biggest thing that I could suggest is that when we look at this list of services is to be aware of how they can fit together. Throughout the rest of this course, we will look at a number of patterns, a number of diagrams, and show the kinds of ways that we might see these services used in conjunction with other services for the sake of creating reliable, performant, cost-effective, secure, and operationally excellent architectures within AWS. This module is based on the reliability pillar of the well-architected framework. Here, we will review architectural patterns for improving the availability and resilience of our applications and the durability of our data. For many services, enabling a high degree of availability will ensure the satisfaction of end users as well as the health of our bottom line. In this lesson, we will discuss high availability, how to calculate service availability, and how to plan for applications to be truly highly available. Now let's talk about designing for availability. So there are 5 practices for availability that we can learn from the reliability pillar of the well-architected framework. And that would be 1, using fault isolation zones. And fault isolation zones within AWS take the form of availability zones and regions, so that if any one particular, let's say a data center fails or an AWS facility fails, then by leveraging multiple facilities, multiple availability zones, that failure is isolated to that one, and our application can continue running because we're leveraging multiple zones. And then we have redundancy, so leveraging redundant components. And when we talk about availability, and as we will talk about later in upcoming lessons, the more components we have, the less impact any one component failing will have on the overall application. We can also leverage microservice architecture so that the risk of change is much lower. So when we deploy a microservice, deploying one small service, if there's a failure, we can more easily roll back. There's a lot of benefits to microservices, and then of course we can design those services so that if any one service fails, other services can continue running. We can also leverage a design pattern that we would call recovery-oriented computing, where again, as we talked about earlier, instead of really spending a lot of time and energy and effort into maintaining the underlying infrastructure, if we leverage disposable resources and simply throw it away, then we can allow automated processes such as autoscaling, user data, bootstrapping, configuration management, and so on, to bring those systems back into a known state. And if we need that state to change, we go back to our source of truth. We go back to our machine images to create that new pre-configured state. We go back to our configuration management or user data bootstrapping scripts to create the state that we need when that machine is recovered or replaced. And then lastly, we would have distributed systems best practices, which include things like request throttling and other types of application design patterns like circuit breakers to avoid retry loops and so on. And so the things that we can do to facilitate high availability would be clearly to avoid single points of failure, to create redundancy, not only in our EC2 instances, for example, but also in our data centers or potentially regions. And then, of course, we should automate everything so that we don't rely on humans doing things slowly or mistakenly, right? So the more that we can automate, the more that we can avoid the errors that humans might inject, and the faster and more efficient we can recover from any kind of failure. And then, of course, like we've mentioned earlier, that scalability is key. We should scale when we need to scale. And we can design systems that don't require human intervention in order to scale. They just scale automatically using auto-scaling, using services like Amazon Aurora for RDS, so that the storage plane scales automatically without us having to go and create a new database instance. We should also monitor everything, not just the metrics from EC2, for example, CPU and memory and network I/O, but we should monitor everything within our application. As logs are coming in, we should stream those to CloudWatch logs. We should stream CloudTrail so that we can understand and see changes to our environment. And then, of course, we should build stateless applications. So if an application is storing state, then, of course, now we have more dependencies to rely on. And then especially if that application is storing state locally, now we have an issue of what happens when that state is gone. So if our applications can be stateless, that gives us a much easier ability to scale and an easier ability to decouple other components. And then, of course, we should apply the appropriate patterns where necessary. For example, we should be using certain patterns like circuit breakers where appropriate, or request throttling, where appropriate, so that we can build in more resilience within the application itself and not just rely on the resilience of our infrastructure. Now let's review plan for failure. Amazon CTO Werner Vogels is quoted as saying, "Everything fails all the time," and it's true. And we embrace that rather than trying to prevent that. We have to understand that everything is ultimately hardware-based. Yes, we can get EC2 virtual machines, but those virtual machines are powered by a physical host. Motherboards fail, power supplies fail. Right? If you've been in this industry for more than a month or so, you've probably seen a deployment fail. They happen, right? We could see failures because of an increased load and the inability to handle that increase in load or demand, right? Our application could receive invalid data that we might call poison pill data, right? An attacker could send data that is unintelligible, and if our application can't handle that data, if it's expecting one format and getting another, then that could potentially cause an application to crash. We could have credentials expire, and now our application can't reach some other dependent service, such as a database or a third-party API. We could have dependencies fail, where our service depends on something else that is now unavailable. We could have just the general underlying infrastructure failures of various types. And so the idea here is that we're not trying to necessarily prevent any of these. While it would be nice if they never happen, as a solutions architect designing systems, our goal is not necessarily to prevent these things from happening. Our goal is to understand that they can and to design a system that can mitigate these failures, right? So again, we are embracing the fact that these will happen and that we're building a system that can tolerate and mitigate these failures rather than causing a cascade. And so as we are designing systems, we should be asking ourselves a number of questions. The more questions you ask, the better. For example, what happens when an instance terminates? Whether it was terminated on purpose or by accident as a result of autoscaling, does the termination of that instance cause something else to fail? Does it cause our application to be down? What happens when a disk becomes full? Does that cause data to be corrupted? Does it cause a service to fail? What happens when the network link is unavailable? When data transmission slows? What happens when a client is sending or receiving data at 1 byte per second? Does that cause network connections to stack up and then exhaust the available ports and make that server unavailable? Or does our application recognize that a client is being slow and then just terminates the connection? What happens when an entire data center is offline? Do we have the ability to leverage a second data center in a second availability zone? What happens during a DDoS attack? Are we the fly under the hoof of the elephant and we get squashed immediately at the first sign of trouble? Or do we have the ability to mitigate those type of attacks? What happens when a security group rule is changed or some other item within our infrastructure is misconfigured? Does that cause an outage, or are we able to mitigate that as well? What happens when authorization is revoked? Maybe we have an application running on EC2 or within Lambda or within ECS. It doesn't really matter, but if that particular application needs access to other Amazon resources like S3, DynamoDB, Simple Queue Service, and so on, what happens to that application when the authorization is revoked? So again, for every component within our infrastructure, we have to ask, what happens when this fails? What happens when it becomes somehow unavailable due to a misconfiguration, a failure, or an authorization issue? And the more questions we can ask, the better. For applications leveraging networking in AWS, the architecture begins with the network with Amazon VPC. In this lesson, we will discuss how our network topology contributes to a more resilient infrastructure. Now let's talk about fault isolation. Remember that within AWS we have a number of mechanisms that we can use to isolate faults to different parts of our infrastructure. And so first we have regions. And within those regions we have availability zones. And remember that an availability zone is analogous to a collection of data centers, right? So within the availability zone, we can place our infrastructure, our subnets, our EC2 instances, our EBS volumes, and by leveraging multiple availability zones, if we lose a particular device, if an entire data center or availability zone becomes offline, then we still have other zones. And so by leveraging multiple availability zones, we can isolate the faults to that one zone, and our application running across those multiple availability zones can continue to run. We can mitigate the faults by isolating them to those zones. And then, of course, we could take that a step further and leverage multiple regions. Again, that other region also leveraging multiple availability zones. And so now any particular fault is isolated per availability zone and per region. And so here, those availability zones are giving us that geographical, physical isolation, allowing us to be resilient to the loss of a data center. And remember that in an architecture like this where we might be using multiple regions, that regions are and should be treated autonomously, that the great majority of AWS services like S3, DynamoDB, Simple Queue Service, and so on, are completely independent region by region, that any one region can become offline and that service will continue to run in all of the other regions. And so we should be building and treating our services the same way. Now let's also remember that for applications that run on EC2 or applications that might leverage, say, Redshift or Elasticache or RDS or AWS Fargate, that we may very well need a VPC in order to make that happen. And so Amazon VPC gives us the ability to create isolated networks, and in order to choose the availability zone, when we launch an EC2 instance or an Elasticache or RDS instance, we don't just launch it into the VPC, we launch it into subnets. And subnets are specific to an availability zone. And so we might create public subnets that have access to the internet. We might create private subnets that don't have access to the internet, right? And so by creating subnets in a particular way, we can then enable our network to allow us to place instances across multiple availability zones. So in that regard, as far as networking within AWS is concerned, remember that VPC is providing logical isolation. So I create my VPC, and then out of the box, by default, it's completely isolated from all other networks, from other VPCs, from the internet, and from my on-premises network. It's a safety-first kind of mechanism. And then, of course, subnets provide isolation between tiers. If we have multiple different tiers, perhaps public tiers for our load balancer, private tiers for applications or databases, then the subnet will give us isolation between those tiers and allow us to customize firewalls for the purposes of that tier. And of course, they also give us that logical mapping to that physical zone, so that by choosing the subnet, we then choose the availability zone. So when we create VPCs within AWS, we should consider how the creation of that VPC will affect the applications and the capacity of those applications that are being deployed within that VPC. So a general best practices for VPC is to choose our IP address ranges wisely, and so that we should choose an IP address space that allows us to create more than one VPC per region. We should also consider the ranges that we're using for all of our other VPCs across every region that we might be using. And we should consider the ranges that we're using on premises as well, right? We should consider the VPC ranges that we're using across our various accounts, right? Because all of the networks that we create, we may want to peer them in some way, whether it's within one region or across regions. We may want to create VPN connections from on-premises. So we need to be mindful of the ranges that we choose so that we don't prevent ourselves from being able to create peering connections or VPN connections. And then in terms of our IP addresses, we need to understand that like if we place an elastic load balancer, for example, the elastic load balancer will automatically scale. But in order to do that, every time it scales, every time it adds a node, it uses an IP address from our network. And so if we create a subnet or a VPC that's too small with not enough IP addresses, then we could prevent our load balancer from scaling. We could prevent our application from scaling if we don't give ourselves enough IP addresses in our VPC. And so when we are choosing, how large to make our VPC, whether we use a /24, a /20, or a /16, it's generally better to err on the side of larger versus smaller CIDR ranges, simply so we don't prevent ourselves from scaling. So remember, in terms of VPC, that our application is running on infrastructure such as EC2, RDS, or Elasticache instances, and those are underlied by the VPC, that the VPC forms the foundation on which those instances run. And so the VPC is the first step, creating a VPC that then allows us to leverage multiple availability zones for the sake of fault tolerance, which then gives us a higher degree of availability. Now let's discuss resilient configuration. So remember that the VPC underlies our infrastructure. And so in order for our infrastructure to be resilient, our VPC and the configuration of our VPC needs to be resilient. And also remember that in the shared responsibility model, the configuration of AWS resources is our responsibility. And so as an example here, when we think about internet connectivity within a VPC, that the resilience of that connectivity is our responsibility. And so in this example, we're leveraging two availability zones. We have a public subnet per availability zone, and we have private subnets per availability zone. In order to gain internet access, we'll of course have an internet gateway. And then in order to allow the subnet or instances within the subnet to communicate with the internet, we need a route table. And of course, that route table needs to be associated with those subnets. And so here at this point, we have one route table that is being applied to multiple subnets. And so now, as a result, instances in those subnets can communicate directly with the internet. Now, if that's what our application really needs, now we need to start asking ourselves some important questions. First, we consider that the internet gateway itself is inherently highly available. It automatically scales, it's fault tolerant, it's redundant. All of those good things are already built in to the internet gateway. But what happens when the route table becomes disassociated from a subnet or both subnets? What happens if the route table becomes misconfigured? In this example, because we have one route table, if it becomes misconfigured in a way that removes internet access, then all of our instances across all of these subnets will then lose internet connectivity. So here, one way to fix that would be to leverage multiple route tables, one route table per subnet. even though each route table would essentially duplicate the same routes, we could then answer that question. What happens when any one route table is disassociated? Well, then that fault is isolated to that one subnet and one availability zone where that route table was applied, right? If it's misconfigured, the fault is isolated, right? And so in this example, we can achieve a much higher degree of availability and fault tolerance by leveraging independent route tables. Now, one argument to this is that you're creating more things, and more things requires more management. But keep in mind that we have automation tools to help us with that. We're not building these things manually. We're not building individual route tables manually. We're not duplicating routes manually in the console. That the ideal practice, as we will talk about more throughout this course, is that we leverage the tools of automation like CloudFormation, Ansible, Terraform, and the list goes on. So the tools are there for an example like this, and so that multiple route tables per subnet is not really a problem. The other argument to using maybe one route table as opposed to two could also be that we have the tools to manage the processes by which changes are made, right? So we have processes in place that we can ensure the right level of access so that those kinds of things don't necessarily happen. And whether you use one route table or multiple route tables is up to you. I'm not necessarily saying that either approach is right or wrong. I'm saying be aware of what can happen when you use one versus multiple route tables. And one last note here is to remember that this is more as much of an example of configuration as it is specifically about internet connectivity, that misconfigurations can happen anywhere. A misconfiguration could happen not just on a route table, but on network access control list, on security groups, on S3 bucket policies, right? So the idea here is that I'm trying to draw your attention to the fact that a failure could occur because of a misconfiguration somewhere, and we really want to understand, we need to be asking ourselves, what happens when this component is misconfigured? How will that misconfiguration or disassociation affect our application running on those resources? Now let's talk about the resiliency of our VPN connections. In this example, we have our corporate data center and we have a VPC in an AWS region. And we want to create a VPN tunnel between our on-premises or our data center location and the VPC. And so in order to do that, we would create a customer gateway on the on-premises side. We would create a virtual private gateway on the VPC side. And between those two, we can create a VPN tunnel. And we'll know that our traffic, even though it's going over the internet, it's encrypted in transit using IPsec encryption. Then, of course, using the previous example, we could apply multiple individual route tables to our subnets so that any misconfiguration of any one route table is isolated to that zone. And using those route tables, we can then communicate from on-premises to EC2 or RDS within that VPC using private IP addresses and encrypted communications. Now, keep in mind that any one VPN connection is comprised of two tunnels. And that's because the virtual private gateway on the AWS side is powered by physically distinct routers in physically distinct facilities. So on the AWS side of things, we already have resilience. AWS could lose any one device and still have another device. So if we lose one tunnel because of a failure in Amazon, we still have that second tunnel. But we need to ask ourselves, what happens when our customer router fails? In this example, if we lose the customer router, or what happens when the customer internet connection fails, then we would be without a VPN connection. If our single router fails, then we would lose that VPN. And so the solution to this is to leverage multiple customer routers and creating multiple VPN connections. Each connection has 2 tunnels. If Amazon loses a device, we still have another 3 on the Amazon side. If we lose a device, we still have another 1, right? And so here in this example, if we need a reliable, resilient VPN connection, then we can achieve that through multiple customer routers. Now, in order to truly achieve, automatic failover from one VPN to another, those multiple routers would need to be configured with BGP. We could also leverage redundant internet connections. If we really do need solid, reliable connection over VPN, then we should also consider the fact that if we're relying on one internet service provider, they could fail, right? So by leveraging multiple internet connections, if any one of them fails, we could fail over to the other. Now let's talk about direct connect resiliency. Within AWS, of course, we have the ability to create direct connect connections, which is a dedicated fiber connection, giving us 1 or 10 gigabits per second throughput into or bandwidth into an AWS region. And of course, in order to make that happen, we would have our customer gateways, our routers on premises, and then leveraging a direct connect location, we would then establish that direct connect connection, partnering with some service provider to run a line from on premises to the direct connect location. And then from there, we could create, if we wanted access into our VPC, we would terminate using a private virtual interface, we would terminate a VLAN into our VPC. We could also use Direct Connect to access Amazon services like S3 or DynamoDB that live outside of the VPC using a public virtual interface. And of course, we can terminate a VLAN into that as well, so that any one Direct Connect connection can be divided into VLANs, some VLANs terminating into VPCs, others terminating into the region in general, so that we can access Amazon services that are generally available through public IP ranges. And so now that we have this set up, we need to ask ourselves, what happens when our customer router fails? Well, as we've seen from earlier examples, we need high availability in that as well. And so in this example, we could leverage BGP to fail over from one customer router to a second. So we would have 2 customer routers. What happens when that direct connect connection fails? So if the connection fails, then we no longer have that direct dedicated fiber connection. One possibility is to fall back to VPN. So we could add high availability to our direct connect by leveraging a failover to VPN using multiple VPN connections, each having 2 tunnels. And of course, all of this, the customer routers and all of these connections would need to be configured with BGP. Now, if that's not enough, let's say that we have a particular scenario that requires a level of bandwidth, throughput, or network performance that VPN could never meet. Then we could leverage redundant connections. And so just like we have the one connection that's terminating into private and public virtual interfaces, we could establish a second direct connect connection. Again, that one terminating into private and public virtual interfaces, divided into VLANs. And so then, of course, we could go even further and ask, what happens when the direct connect point of presence fails? When the actual facility that houses the AWS routers that manages, that powers that direct connect connection, what happens when our provider fails? We're getting access into the direct connect point of presence through some service provider. If their connection fails, then we could have an issue. And so in this regard, we could leverage multiple customer routers, multiple direct connect connections, and multiple direct connect locations. each location having redundant connections. We could also leverage redundant service providers, right? And so we could add a higher degree of availability with redundant customer routers, redundant direct connect connections, redundant direct connect facilities, and redundant service providers, so that if any one thing fails, we still have something else. Achieving reliable infrastructure and applications in AWS requires consideration of capacity and application and database resilience. In this lesson, we will review a number of diagrams that illustrate principles and techniques to improve the resilience of our applications. Now let's talk about application resiliency. Let's take an example of running an application on one EC2 instance. So here we have one availability zone, one EC2 instance, and on that instance we're running a monolithic application along with a database, and we're serving static content. Our users come through our internet gateway directly to our instance. Now, there's not necessarily anything wrong with this example. There are plenty of websites out there. I can think of a dozen different WordPress or Drupal installations where this is a classic design. But we should think about the consequences of running an application in such an architecture, right? We have to ask ourselves, what happens when the instance fails? In that regard, if the instance fails, we are offline, our system is down, our end users cannot get what they're looking for until that machine is replaced, until those processes and the data is put back and restored, right? And so in that regard, the availability of our system depends on the time it takes to replace the instance, to recover the data, to install any dependencies that might be necessary, to configure our processes, and then start those processes. Along those lines, the recovery time will be increased with manual operations because it takes humans time to do things. Recovery time will be decreased through automation. Now we need to ask ourselves, well, what about the data? We know we need to recover the data, but where is the data stored to begin with? How do we recover that data? We need to think about, are we using instant stores, EBS volumes, or something else? With an instant store volume, in this example, the data would just be gone and unrecoverable. And so we can take this further, and we could offload static content to S3. That would reduce the load on our EC2 instance. That would allow us to, as we will see later, we could potentially fail over. If our instance fails, and while it's being recovered, we could fail over to a fail whale page within S3. We'll see an example of that later on, right? So again, offloading static content can reduce the load on the server. And now we need to ask again, how do we recover from failures in our application or the process? How do we recover from an instance failure? So again, if the instance fails, then we can simply terminate that instance. And remember that within EC2, if we have our root volume powered by EBS, that root volume will default to delete on termination equals true, which means that when we delete that terminate that EC2 instance, the EBS volume will also be deleted, right? So that's a good thing. If we are regularly rolling EC2 instances over through autoscaling or other processes, what we don't want are hundreds or potentially thousands of EBS volumes being orphaned and left behind. But our data here, if we have our data for the database on a separate EBS volume, then the DB data will survive. And so that when we bring that EC2 instance back, We can do that using a custom Amazon machine image so that the great majority, if not everything we need, is already installed and ready to go, right? So the Amazon machine images then will provide that known pre-configured state that represents exactly what we need for our application to do its job. So we bring that machine back to life. We can then use user data, bootstrapping scripts, or configuration management to update code, to start processes. We can use those same tools to reattach and remount an EBS volume so that the database data is now once again available to the database engine. But now, how do we recover from data volume deletion, right? How do we recover from the failure of an availability zone? These are also things we need to consider. We can leverage EBS snapshots to recover that data, right? So snapshots can help us restore the volume, not just in the same availability zone, but we could also restore that volume to another availability zone if we needed to. So again, those Amazon machine images are providing that pre-configured state, and user data is providing bootstrapping, and together these can lower the time it takes to recover from a failure. And again, snapshots are also providing increased durability so that if we lose our volume, we still have our data available. Now we can take this a step further and leverage the elastic load balancer. So the elastic load balancer gives us a single consistent DNS endpoint, and then it distributes incoming traffic across multiple EC2 instances. So that way, if any one instance fails, we still have another instance. And we don't have to worry about, sending our end users directly to the instance where the IP address can change. Right? Keep in mind that the elastic load balancer will have a network footprint in our public subnets. So going back to what we talked about earlier with our network, the VPC underlies this infrastructure. And so we've created a VPC here that allows our load balancer to leverage multiple availability zones. We'll also use auto-scaling so that if any one machine fails, auto-scaling can replace it, right? So auto-scaling enables self-healing environments. Remember that auto-scaling is not just for scaling to meet demand. Just as important, it is for creating those self-healing environments so that if an EC2 instance fails, auto-scaling can terminate it and replace it. That's an example of recovery-oriented computing. We're not trying to fix this one machine. We're not going to shell in and play doctor and try to save it. We are going to allow it to be replaced because it's a disposable resource. So here, the availability of this application is improved through, again, leveraging multiple availability zones, through leveraging redundancy in our EC2 instances, multiple instances, through leveraging auto-scaling to replace instances that might fail, and that auto-scaling is leveraging a pre-configured Amazon machine image so that as those machines come to life, they have most, if not all, that they need ready to go in order to get that service back online. Now let's review database resiliency. Now within AWS, we can of course run a database on EC2. Plenty of customers run plenty of applications by managing their own database engine on EC2. But we need to understand, how we achieve resiliency and, the pros and cons of doing it ourselves versus leveraging a service like RDS. And so in this example, we have multiple EC2 instances all communicating with one database. Right? So now we need to ask all those questions. What happens when it fails? What about the data and all of that? Well, ideally, we could have multiple instances with ongoing replication so that we can automatically fail over from a primary to a secondary at any time, right? So that if our primary fails, we can then simply fail over. And we would ideally have that automated so that we don't require any kind of manual intervention in order to actually fail over. And we can leverage auto-scaling to replace the previous primary that failed. And then the replacement would then become the new secondary. We could leverage custom AMIs that are fully pre-configured to shorten that time. So we have to ask ourselves, what does the do-it-yourself approach on EC2 really entail? This isn't about right and wrong, and I don't generally like talking in terms of right and wrong. What I'm drawing your attention to is simply the consequences of doing, one thing versus another. And there may be times, and there are plenty of use cases out there for running a certain database on EC2. Perhaps your application generally has the need for running a particular database that is outside the scope of what's possible with RDS. And if that's the case, then we need to be aware of our responsibilities. So the DIY approach on EC2 means that we carry the full operational burden. We, as the customer, are responsible for patching the operating system, for keeping the operating system secure and up to date. If there's a new vulnerability discovered, we have to patch that. And if we don't, and then we are the subject of an attack, that's on us. That's our responsibility. We are responsible for upgrading the database engine. We are responsible for the security itself, the secure configuration of the operating system and the database engine. We are responsible for replication and failover. We are responsible for performing backups and ensuring that we actually have the ability and we have a known process in order to recover from those backups. So we are responsible for everything in that regard, everything but the physical infrastructure. Now, by leveraging the relational database service, we can offload a lot of that responsibility, the great majority of it, to AWS. So with RDS, we can create a primary, and if in production, the production best practice is to launch that as a multi-AZ deployment so that AWS creates and manages both the primary and the secondary, as well as ongoing synchronous replication, right? We can also leverage RDS snapshots for greater durability. That's all built in. So we send our writes to one endpoint, and if that endpoint fails, AWS will use DNS to fail us over from the primary to the secondary. So again, if the primary fails, AWS will promote the secondary to be the new primary. We then, through DNS, start talking to that new IP address, and then AWS will automatically, the relational database service will automatically replace the old primary with a new instance that then becomes the secondary. So that whole process now, and the setup, the creation, the ongoing management of all of that is now offloaded to AWS. So the benefits of RDS is that we now have very little operational burden. We are now only responsible for the data, for our schemas, and for writing SQL queries. So we can focus, our team can now focus on adding value to our application rather than being burdened with the low-level details of managing a relational database. Right? So again, AWS is now responsible for patching the operating system, for performing DB engine updates, the operating system security, database engine security, failover, backups, replication, and so on. Right? And so again, as a result, we get to focus on adding value to our application, writing our queries, and optimizing our data and our schemas. With RDS, we have a number of great options that can help increase the durability of our data. When we run the relational database instance in a multi-AZ deployment, we have 2 copies of the data that are live. that would be the primary and the secondary, so that if the primary fails, we still have the secondary. Those are, with synchronous replication, we have two copies of the data that are living and available. If we lose both, we still have snapshots, right? So within RDS, remember that RDS automated snapshots are performed once every day. We get to choose during which window, at what time, those snapshots are done. Generally, we will choose a window of time where our application sees, the lowest amount of traffic. We can also perform a point-in-time recovery, right? So we can generally restore a DB instance using a snapshot. We can use the snapshot to restore a database instance to within the last 5 minutes if we need to. We can also perform what we would refer to as manual snapshots at any time. Even though we call them manual snapshots, those can be automated by our own tools. Keep in mind that we can also copy snapshots to other regions. So if we wanted an even higher degree of durability, if we wanted to put some geographical diversity in our data and have that data available in a second region, then we can leverage manual snapshots to copy to that other region, right? Now, we can create manual snapshots from automated snapshots. And so automated snapshots cannot be copied to other regions, but we can essentially create a manual snapshot from an automated snapshot and then copy that manual snapshot to another region. In that regard, what goes along with the availability of an application is not just whether or not we have machines running, but also whether or not we have copies of the data that can be recovered. And so to get there, we need durability in our data, and greater durability is achieved in this example through multiple regions, through cross-region snapshot copies, and remember that snapshots can also be shared across accounts. It's a very common pattern, and even recommended pattern, that organizations leverage multiple accounts for the sake of isolating resources. And so you may have one account that is doing, production traffic, but another account that's designed for backing up that data in case the production account is compromised. Now let's talk about capacity planning. In this example, we have an auto-scaled fleet of EC2 instances behind a load balancer. And for an application like this, we're going to be receiving a number of requests, some number of requests, being handled by some number of EC2 instances. And we have to ask ourselves, the consequences of losing any particular part of our infrastructure. And now in this example, because we are leveraging a managed service, we can rely on the fact that the elastic load balancer is inherently scalable and fault tolerant, and all of those good things are built into that managed service. But there is a configuration issue we need to be aware of. The elastic load balancer, while it is inherently scalable, the classic and application load balancers sometimes don't scale fast enough. Yes, they can scale, but sometimes the rise in our demand outpaces the ability of the load balancer to scale to match that demand. And so in those cases where we know that when we can predict and know that we will have a significant rise or surge in traffic, then we can request that AWS pre-warm the load balancer to go ahead and get it to scale out before the demand is actually there. And now once those requests are coming through the load balancer and being distributed among our back-end instances, now we need to start asking ourselves some questions, right? How do we scale? Well, auto-scaling can enable us to dynamically scale based on demand, scale out to meet that demand, scale in to save money. But we also need to ask ourselves, what happens if an EC2 instance or an availability zone fails during peak demand? can the remaining servers or the remaining availability zones handle the current load? In this example, if we only had 2 instances across 2 AZs, then the loss of any one instance or an AZ would result in 50% loss of capacity. Can we meet our SLA? Can we continue to deliver traffic under the current load with only 50% of capacity? So in this regard, with only 2 availability zones, each zone would need to meet 100% of capacity. So if we scale the number of instances, so in this example now we've gone out to 4 machines, and again we ask that question, what if during peak demand we lose an instance, an EC2 instance fails, then that would result in the loss of 25% of capacity. Can we meet the current demand with the remaining 75%? Probably. The answer to that question would most often be yes, probably we could. But what if the entire availability zone fails? If we only have 2 and we lose the AZ, then we would result again in a 50% loss of capacity. Can we meet SLAs? And so now let's take it a step further. Let's look at leveraging 3 availability zones. And now in this example, we have 6 EC2 instances across 3 availability zones. And so again, what if during peak demand we lose 1 instance? The loss of 1 instance would result in a 16% loss of capacity. So you can see the pattern here is that the more instances we have, the smaller the impact when we lose any one instance. What if we lose an entire availability zone? The loss of any one availability zone would only result in a 33% loss of capacity. Can the remaining 84% or 66% fulfill the current demand? Right? These are the kinds of questions we need to be asking ourselves when we design an architecture, right? So for the sake of capacity and ensuring that the loss of any one device or availability zone still gives us enough to meet that demand, in that regard, the more the better. But we also, as we will talk about later, need to balance that with performance and cost. Now let's talk about monitoring for availability. The only way that we can truly achieve the highest degrees of availability is to monitor our infrastructure. Within any given infrastructure, we need to be asking, how do we know what our current latency is? How many healthy hosts exist behind the load balancer? What's the average CPU usage right now? And not just historically, but more importantly, right now, we're looking at monitoring to be real time. What about disk and network I/O? And so the only way to monitor this is to collect those metrics from those services. And to do that, we can leverage Amazon CloudWatch to collect those metrics, right? So the Elastic Load Balancer can feed in certain metrics. Our EC2 instances, both individually and in aggregate through autoscaling, can send metrics to Amazon CloudWatch, right? So in that example, the Elastic Load Balancer would report the number of healthy hosts that are currently registered behind it. It would report the status codes, the counts for current status codes, 200s versus 400s, 500s, and so on. The current latency as measured between the load balancer and our backend instances. Typically, you might say that as the latency increases, that would indicate that the current demand is also increasing. What about the current request count? We might want to use that for, analytics just to get an idea of the current load, the current demand, how many visitors we're seeing, and so on. We might want to correlate later the request count with other things such as latency, EC2 reports, and so on, so that we can see is there a relationship as the number of requests rises. Do we also see a correlation in CPU or network I/O and so on? EC2 will report things like CPU utilization, disk I/O, network I/O, and so on. The EC2, the hypervisor, is performing a number of status checks, and if those fail, those will be reported to CloudWatch as metrics. And then we can leverage alarms and then use those alarms to send notifications so that we know about issues, right? So we need to be asking ourselves, how do we know, when to scale? When an incident arises that we might need to address, right? So again, we can leverage Amazon CloudWatch to collect these metrics. We can create alarms. So for example, we might create an alarm to trigger some action or notify us when CPU utilization is greater than 80% for more than 5 minutes. We might use that alarm to trigger auto-scaling and add machines in order to bring that average CPU utilization down below 80%. We might create other alarms, such as, we might want to be aware of when the average load balancer latency is greater than 700 milliseconds for some period of time. We might want to do something when the maximum number of healthy hosts is too low for some period of time. And so either way, any of these alarms can be used to trigger a topic within the simple notification service. And so we can subscribe to that topic in a number of different ways, for example, email, HTTP, text message, and so on. So we might want to get an email about some of these, or we may want to trigger third-party services. So HTTP subscriptions could be used to trigger those third-party services such as PagerDuty. So not only are we monitoring the infrastructure itself, our auto-scaling groups, our individual EC2 instances, the load balancer, but we also want to monitor external endpoints. We want to ensure that the endpoint is delivering the proper response, say a 200 series response, regardless of how that endpoint is actually implemented. We might have one endpoint running powered by EC2 behind the scenes. Another endpoint could be powered by API Gateway and Lambda behind the scenes. But either way, we want to monitor the endpoint itself from the outside. We want to know that if we send a request to that endpoint, that it's going to return a particular response, right? So in this example, all of our applications could fail across all of our instances. And then as a result, there are no healthy instances with which to send a 200 level response, right? The security group between the load balancer and our EC2 instances could become misconfigured and prevent the load balancer from communicating with our fleet of EC2 instances. I've seen it happen. I've been there. I've done that. It can happen, so we have to consider those kinds of things. And what happens when that, in those cases? How do we know that, something is going on as, from the perspective of our end users? How do we know the service as a whole is working? And then what happens when the service as a whole fails? We can leverage Amazon Route 53 health checks so that Route 53, when we configure a health check, Route 53, because it's powered by edge locations, it can use those edge locations to send a request to our endpoint. So in this example, we can configure a Route 53 health check to send requests from various edge locations to our ELB DNS endpoint. And then if that endpoint fails, whether it's a security group issue or an application process issue, doesn't really matter. But what matters here is that to the perspective of the Route 53 system that's making that request, it's not getting the right response. It might now be getting 500s instead of 200s. And so in that regard, what we can do, one option, is to fail over to a static website. We can create, with S3, we can create a bucket that is configured to host a static website. And then if our load balancer fails, we can fail over to what we might call a fail whale page. So if you remember the early days of Twitter when they were having a number of outages regularly, what they did was if the service failed, they presented the fail whale and saying, hey, we're sorry, but try again. It's better to give them something. It's better to give our end users, hey, I'm sorry, please try again, than a blank white page or a timeout. And so in this example, again, if our dynamic endpoint, our load balancer is failing, then we can move our users to a static website, and we can leverage Route 53 failover routing to do that. Right? So remember that Route 53 supports a number of types of routing: latency-based routing, geographic routing, and of course failover routing, so that if one endpoint is not working, we can automatically switch to another endpoint. Now let's review multi-region architectures. So within AWS, of course, we have the ability to leverage multiple regions. And of course, we can run those multiple regions in active-active or active-passive modes. And so the way that we would go about doing that would be to, of course, in one region, we may have a load-balanced endpoint in one region and maybe another load-balanced endpoint in another region. They don't necessarily have to be built in the same way. Again, one region could be powered by EC2, the other region could be powered by API Gateway and Lambda. That doesn't really matter. What matters is, according to the Route 53 health checks, is the endpoint as a whole giving us the responses that we expect? And so our users are ultimately, through their browser and whatever client they're using, they are making DNS queries to Route 53 for the domain name that they're looking for. And Route 53 is responding with an IP address that represents the endpoint that we want them to go to. And so in order to configure this, we would create within Route 53 a hosted zone. And in that hosted zone, we would have a number of records. So in this example, we would have, let's say, example.com as a primary pointing to US West 2, as the target there would be an alias record to the DNS endpoint of the load balancer in the US West 2 region. We would have a second record for example.com, and you'll see here that it is also an alias record for the DNS endpoint of a load balancer in US East 1. And you'll notice here that the routing policies are both failover and that the record types are primary and secondary. And so Amazon Route 53 will make regular health checks to both endpoints. And then, of course, our users are being forwarded to the primary endpoint. Once that primary endpoint fails and is no longer sending the proper responses, Route 53 can simply fail over to the secondary endpoint. And so that's an example of how we can configure multiple regions in active-passive. And of course, it's possible to take this a step further and combine both geographic or latency-based routing with failover routing, so that our users, ultimately, when all is fine and healthy, our users always go to the endpoint that gives them the best latency. But if any one endpoint fails, they then fail over to the other endpoint. So it is possible to combine different routing methods within Route 53 to ensure that users are getting the best latency and the ability to fail over. This module is based on the performance efficiency pillar of the well-architected framework. Throughout this module, we will discuss how our decisions can affect the performance of networking, computing, storage, and databases, as well as our software development process. Since the network underlies our infrastructure, performance of the network underlies performance of our infrastructure and our applications. In this lesson, we review a number of principles and service details that can help you design performant networks in AWS. Now let's review networking performance. So starting with the performance of inter-instance communication, there are a number of things that we should keep in mind. When we look at our infrastructure and we realize that some of our instances will be in the same availability zone, some instances will be across in other availability zones. So anytime traffic crosses the AZs into another availability zone or even another region, we will incur additional latency. So if you are designing or planning for an application that is latency sensitive, we should keep that in mind. And we'll talk more about that point and options in an upcoming lesson. Keep in mind that EC2 instances in the same availability will generally have lower latency. And so sometimes there is the need to sacrifice high availability and resilience to the loss of a data center for the sake of getting the absolute highest performance out of our network. Another thing that we can do to increase the performance of our network, to increase the performance of communication between instances, is to leverage enhanced networking. Enhanced networking will generally improve the latency, packets per second, total throughput between instances. This is available for many instances, but not all. Keep in mind that some of the later generations will support enhanced networking, but some of the earlier generations of EC2 instances will not. And it's also only available on HVM type virtualization. And now in some cases, some Amazon machine images for some instances will already have enhanced networking enabled. Another thing that we should keep in mind is that the number of rules in our security groups will eventually contribute to degraded networking performance, right? So keep in mind that any one EC2 instance could have a number of different security groups attached to it, and each group could have a number of rules. And so altogether, the combination of those could contribute to degraded performance. The general rule of thumb here is that if you ever find yourself asking for an increase in the limit of security group rules, then you will probably at that point start to see a degradation in your network performance. And at that time, it would probably be better to re-architect your security group rules rather than asking for an increase in that limit. Now, another thing that we could do to improve the performance of our network is to enable jumbo frames. And so for those of us who might not have a background in networking, when data is transmitted between two hosts on a network, the data is broken up into packets or frames. And so the standard frame size says that the amount of data that a packet is carrying will be 1,500 bytes, right? So that's 1,500 MTU, or the MTU meaning maximum transmission unit. How much data will we send in this frame? And so Jumbo Frame says that we're going to increase that to 9,001 bytes. And so the idea here is that when we're transmitting data, each of these packets or frames, they have to be encapsulated with headers information, and then when they get to their destination, they have to be unwrapped, the data extracted. So the more frames, the more overhead. Therefore, if we increase the amount of data, that means that we have fewer frames. The fewer frames, the less overhead. The less overhead we have in our network transmission, the better the performance. So when we have two instances within the same VPC, we can rely on jumbo frames to improve the performance between those two instances, right? So this is especially good for clustered types of services, or anytime you're communicating between EC2 and a database, or let's say you have a cluster database system like Cassandra or Mongo, and those nodes need to gossip back and forth. Jumbo frames can really help in that situation. But we do need to realize that jumbo frames only work inside the VPC. So when our network traffic tries to reach the internet, if we have jumbo frames enabled, the internet gateway, in this case, will see that jumbo frame and say, hey, I can't send a frame that large out to the internet. I have to create smaller frames out of that. I have to divide that down to the standard MTU, which is 1,500 bytes. And so that process is called fragmentation. So the internet gateway will fragment those jumbo frames down to smaller frames. Jumbo frames will also be fragmented by virtual private gateway being used for VPN connections. Jumbo frames will also be fragmented by a VPC peering connection. So again, anytime network traffic leaves the VPC, those jumbo frames will be fragmented. Now, some applications may set what we call the do not fragment flag. And if that flag is set on those network packets, then those gateways, the internet gateway, the peering connection, or the virtual private gateway will drop those packets. So keep that in mind, that everything is correct, that your routing, your network access control list, your security groups are all correct, that traffic should flow. And if you still find that traffic is not flowing, don't forget that jumbo frames that are set to do not fragment could contribute to traffic not getting where it's supposed to go. Now, one last thing to talk about in terms of networking performance would be placement groups. Placement groups are a logical grouping of instances that exist in a single subnet in a single availability zone. The idea here is that we want to place these instances as physically close together as possible. When we think about instances being across two different availability zones, that means that the instances are now behind multiple switches, probably multiple back-end routers, and there's a larger physical distance. And all of that will contribute to latency. So the closer we can get them together, ideally if they're even behind the same switch, that will give us the lowest latency between those instances. And that is exactly what a placement group is for. So in terms of best practices for placement groups, it's generally better to launch all of the instances that you need in that placement group at once, because in order for AWS to be able to place those instances as close together, it needs to be able to find a rack within that facility that has room for that many of that type of instance. And so if you launch, let's say that you launch 3 now, and then you try to launch 3 later, you could end up in a situation where AWS says, well, we don't have room for those additional 3. It's also generally a best practice to use the same instance type for the same reason, so that AWS can optimize the placement strategy for finding a host within that facility in order to place those instances on. It's also a better practice to use private IP addresses. Remember that it is possible to use public IP addresses or assign public IPs to instances in a placement group, but if those instances communicate to one another using public IP addresses, then that means that the traffic has to be routed out to a public address space and then back into the placement groups. So that traffic is actually going to end up leaving the VPC and then coming back in, which will add additional latency. So if what you're trying to achieve is absolute lowest latency with a placement group, the only way to do that is to leverage private IP addresses. Now, it is worth noting that you can add instances to the group later. You can stop and start instances, but the issue here is that if you try to add machines later, or if you stop and start them, AWS could return an error saying that they don't have room, they don't have the capacity, because now the placement group essentially narrows the scope into which Amazon is trying to launch those machines rather than just anywhere, right? And another thing here is that you cannot merge placement groups. So if you have 2 different placement groups, you cannot merge those. And if you have some number of instances that already exist outside of a placement group, you cannot move those into an existing placement group. So in order to create a placement group, you have to launch new instances into that placement group. So to recap networking performance, keep in mind that there are a number of things we can do that will contribute to the performance of our network. And that would be enabling enhanced networking, leveraging jumbo frames, being mindful of the latency that could be incurred by cross-AZ or cross-region traffic. And in some cases, especially for high-performance computing, we may want to leverage placement groups. Now let's review the performance of network address translation. Now, we can perform network address translation in a number of different ways. And of course, the reason we do that is because in this example, we have EC2 instances, perhaps running our application, in private subnets. We don't want them to be accessible from the internet directly, but for the sake of doing patches or code updates or calling out to configuration management or reaching some third-party service on the internet, they need to reach out while still being protected from being reached from the internet directly. And so we can use network address translation to do that. And so we can run network address translation on our own on EC2. There's a number of different tools we could use for that. But we have to keep in mind that the performance of that will be dictated by the EC2 instance type, right? So smaller instances like T2s will have generally low to moderate network I/O. In order to improve the performance, in order to avoid that instance becoming a network bottleneck, the only option we have is to transition to a larger, therefore more expensive EC2 instance. So if we replace that instance with a NAT gateway, the NAT gateway will start at 5 gigabits per second worth of bandwidth. It will automatically scale up to 45 gigabits worth of bandwidth. So when you consider that some EC2 instances are capable of 25 gigs, but those are incredibly expensive. They're much more expensive than the NAT gateway itself, right? And so the NAT gateway will generally give us the better performance for a much lower price. Now in this example, so now we've improved the performance and lowered our costs by leveraging a NAT gateway versus running network address translation ourselves on EC2. It is also inherently highly available and fault tolerant. The resilience of this gateway is already built into the price that we're paying rather than us managing it ourselves. Now, in this example, we have two availability zones leveraging one NAT gateway. And so in that regard, we will have the increase in latency across the AZ and, of course, the added cost of the cross-AZ traffic. Another option that we could do here is to add a NAT gateway per availability zone. And we can use route tables per subnet to say that each subnet will use the NAT gateway in its own availability zone. And by doing that, we can increase the bandwidth that's available to that availability zone and improve the latency. In this lesson, we will discuss compute performance and how our decision to use any particular instance type or to leverage containers can help improve the performance of our applications. Now let's review our compute options. Within AWS, we have a number of options for computing, starting with instances. Instances are generally the default for many applications. And within instances, within that option, we have a number of choices in terms of choosing the right size instance for the application that we're deploying. We also have containers. And of course, containers give us a way of securely isolating processes so that we can run multiple applications on the same instance. And by doing that, we can leverage or utilize more of what that machine has to offer. We can ensure that all of the CPU cycles, memory, network, and disk I/O that we're paying for are actually being used, rather than remaining idle, in which case we would be over-provisioned, right? So again, containers allow us to improve the actual utilization of the instance that we're paying for. And lastly, we have functions with AWS Lambda. And functions are a really great option for event-driven infrastructures or tasks that may be performed asynchronously in the background. Functions also give us a very high degree of concurrency. And so now when we look at EC2 instance types, we have a number of different families to choose from. We have the general purpose EC2 instances, which gives us the T2 series, the M3, 4, and 5 series, and these are general purpose, they're mixed use. They're good for a lot of different types of applications. But some applications may be more CPU intensive, some applications may be more memory intensive. So we have other families for that. Of course, we have the compute optimized families, giving us the C4 and C5 series. We have families giving us access to GPUs or high performance computing, the P2, P3, and G3 series. We also have a family that is more memory optimized, giving us much more memory than, say, the M or C series. And that would be the X1, the R3, and R4 series. We also have EC2 instances that are more geared towards internal storage. This would be the i3 and the H1 series, also the D2 series as well. And so it all depends on what our application really needs, right? So when we look at the needs of that application and we go, you know what, this application might need a lot more CPU than it does memory, or this particular application will be doing a lot of random I/O, and so maybe we need more storage capacity. Or perhaps this high-performing computing, maybe we're doing something with cryptocurrency and we need access to a GPU. So in terms of performance, it's all about choosing the right computing solution for the work that's being done. Now let's talk about the performance for instance-based applications. So in this example, perhaps we have an application running on EC2 behind a load balancer. Maybe it's an API or some type of web application. So the first thing that we want to consider is the fact that every component in our infrastructure will contribute to the overall performance, starting with the load balancer. So we would ask ourselves which elastic load balancer is most appropriate for our application. Remember that we have three different types of load balancers. We have the classic load balancer, the application load balancer, and the network load balancer, and they all have their own options and will affect performance in different ways. So the application load balancer provides host name and path-based routing, which may be very useful for our application. The classic load balancer does not offer those, but maybe we don't need that. But keep in mind that both the classic and application load balancers, while they are scalable, there are some times where they don't scale fast enough and need to be pre-warmed. The network load balancer, on the other hand, out of the box can scale to millions of concurrent connections, but it doesn't offer path and host name routing. So it's all about determining what our application really needs and then understanding the effects of that particular load balancer on our application. Now when we move to the actual EC2 instance, we need to keep in mind that, what EC2 instance type will be the most appropriate. The truth is we don't really know. For a new application being deployed to AWS, we don't really know until we try it. We don't know anything until we have direct experience that we can measure through monitoring. So generally speaking, we could expect that we're going to see constraints somewhere, and will that be on the CPU, memory, network I/O, disk I/O? Again, we don't really know until we deploy the application and monitor it, right? So the C4 series, the C5s, the M4 and M5s are generally good places to start. For a new application, one of those series you might choose to start with, and then of course, how do we know? What we're going to be seeing in terms of bottlenecks, infrastructure bottlenecks. The only way we know is to monitor that with CloudWatch. And remember that CloudWatch will collect metrics from the hypervisor for individual EC2 instances, and then for instances in an autoscaling group, CloudWatch will collect those in aggregate across, averages across the entire autoscaling group. And so we should be using CloudWatch to capture those key performance indicators. And we can do that for both infrastructure and our application metrics. So keep in mind that CloudWatch can collect custom metrics. Anything that can be recorded as a number over time can be published to CloudWatch as a custom metric. So we can have our application, or even some secondary process running alongside our application, report a number of things as custom metrics. We could report such things as thread and process count, JVM heap size, garbage collection rates, and other information related to garbage collection. Disk usage. Keep in mind that with EC2, we do get information automatically reported about disk I/O, but we don't get information recorded about exactly how that disk is being used, right? So if we wanted detailed disk usage information, we would have to report that ourselves, writing our own agent. We might also want our application to report the number of concurrent connections. We might report just about anything, perhaps the number of failed authentications we're seeing over some period of time, right? And then, of course, any of these things can be turned into alarms. Any metric we can use to create an alarm, and that alarm we can use to alert us as to whether or not maybe there's an issue happening that needs to be addressed, or we could use those alarms to trigger autoscaling. So one of the keys to performance is to match the current supply with the current demand. We want to avoid being over-provisioned, because over-provisioned means that we are wasting money. Being under-provisioned means that we can't actually meet the current demand. And so leveraging CloudWatch to monitor these metrics and allowing those alarms to trigger autoscaling allows us to match supply with demand. Now, another thing that we can do in this example is, like we've mentioned earlier, by offloading static content to S3, we can then reduce the load on EC2, which would then give that instance more CPU cycles to devote to generating dynamic content. So again, in terms of performance, we need to consider all of the components in our infrastructure: the load balancer, the type of EC2 instance, whether or not we're offloading content to S3, and together as a whole, that will contribute to the performance of our applications. All right, now let's review improving performance with containers. So when we think about deploying applications to EC2, we know that we don't want to be over-provisioned, because being over-provisioned means that we're wasting money. We're paying for more resources than we really need. We don't want to be under-provisioned, because that means that we don't have the ability to meet demand. So the question we should be asking ourselves is, how can we most effectively utilize all of the resources, such as CPU, memory, network I/O, that are available to the instance that we're deploying this application to? And so the answer to that question could very well be to leverage containers with Amazon Elastic Container Service, right? Now, if we're running a single application on an instance, then that may very well mean that we have a significant amount of resources going underutilized. We have CPU cycles going by that are not being used to do work. We have memory that is potentially not being used. We have the potential for network I/O and disk I/O that might not be used, right? So we potentially have more resources than are actually being utilized. And so we can capitalize on that by launching multiple processes. Multiple applications can run side by side on the same EC2 instances by deploying them with containers. And the reason we were using virtual machines for so long is because we needed isolation. But containers give us that. Containers give us a way to run those multiple applications, multiple processes on the same host, sharing the resources of that host, but also preventing those applications from interfering with each other. In that process, in that way, containers are giving us that more efficient use of those resources, keeping those processes isolated on the same host. Now, in this example, we are leveraging the Amazon Elastic Container Service as well as the Elastic Container Registry. And the Elastic Container Registry will give us that secure, private storage for Docker images. And of course, images form the basis of containers. And then the Elastic Container Service is the service that is responsible for scheduling containers and actually placing containers on a fleet of EC2 instances. So in this example, we're only showing one instance, but generally when we use a service like Amazon ECS, we would create a cluster of EC2 instances. Some number of instances could be 2 or 3. It could be 200 or 300 instances in that cluster. And the ECS service is responsible for placing the containers on those instances. So from our perspective, we deploy to the cluster. And ECS is responsible for making sure that some number of containers gets deployed across that cluster. Now, another thing that we can use to even further improve performance is dynamic port mapping. So the question is, how can we place more than one container for the same process or same application on a single EC2 instance? And the answer is to leverage dynamic port mapping with ECS and the application or network load balancer. So when we use an application or network load balancer, we would define what we call target groups. And target groups simply provide a group of targets, in this case containers, to route traffic to. So each container would be a target, and each target is capable of listening on a unique port. And so in this case, say we deploy a container for a particular application. Once that container is deployed, the Docker engine will map a random host port to a fixed port within the container. With Docker Bridge networking mode, Docker is essentially virtualizing the network so that it can map a host port to the container port. So our application could be hard-coded to listen on a particular fixed port, such as 80 or 8080 or 3000, whatever the case is. And then Docker can map that fixed port to a random dynamic port. And then once Docker has assigned that random port, ECS will automatically register that target, that container on that port with the load balancer. So the load balancer knows that it can find that target on that port. And then of course, for that particular application, we could have multiple processes or replicas of that container running side by side, each one listening on a completely different port. So one application has, in this example, 2 containers. And then we might very well have another application also running 2 containers, each one listening on a completely different port, and each one being a target registered behind the load balancer. And now with using the application load balancer, we can create rules to allow that application load balancer to route to those groups of containers based on host name or path. So when it sees a particular path, it knows to route that path to that group of containers. And when it looks to that group and it picks a target out of that group, it knows which port to connect to that target on. So again, dynamic port mapping is a very powerful way of really improving the performance and the utilization of our container cluster, because it allows us to place multiple replicas of the same application on a single instance. It allows us to scale the number of containers beyond the number of instances in our cluster, and that way making much more effective and efficient use of the available resources. Within AWS, we have a number of different storage options, and they each offer abilities to improve performance depending on the type of storage. In this lesson, we will review the performance characteristics and options for block and object storage. Now let's review our storage options. When we think about performance of our storage, whatever it might be, whether it's block or object or file storage, it helps to be familiar with all of the options we have available and the nature of those options. So within AWS, of course, for block storage, we have a number of options. We have the Elastic Block Store service, in which we have SSD general purpose volumes. And of course, those are based on SSDs, but they operate at a baseline performance of 3 IOPS per gig. So a 100 gig volume would give us about 300 IOPS. Now, for some applications, that might be fine, and other applications, that might not be enough. So we also have the SSD provisioned IOPS. And so provisioned IOPS says that we can allocate both storage and a certain degree of IOPS for that volume. So if we do need 100 gigs, but much greater than 300 IOPS per second, then we could go with provisioned IOPS and guarantee that we get a consistent performance for that volume. Now for random I/O, the SSDs are a great option. They will give us good performance for random I/O. But for other applications where throughput or sequential access is more important, then we have the hard disks. And in that regard, we have the throughput optimized and cold storage. Now, throughput optimized is a great option where you need a lot of a high throughput volume rather than I/O. In that regard, with the HDD throughput optimized storage, you can get upwards of 500 megabytes per second. And now we also have the EC2 Instant Store volumes. And keep in mind that those, we have a number of options, especially with the storage optimized compute instances. Many of those are based on SSDs, but they are ephemeral. And the trade-off there is that while we don't have any type of built-in persistence, we don't have the ability to take snapshots, we do get a very high degree of IOPS. In some cases, we could go beyond 300,000 IOPS with EC2 Instant Store volumes. Now, we also have file system storage using the Elastic File System. EFS gives us the ability to create a volume that is shared among multiple EC2 instances. Remember that with EBS, the Elastic Block Store, any one volume can only be attached to one instance at a time. But if we need that volume to be attached to multiple instances, then we can look to EFS, the Elastic File System. And then we have object storage. And of course, our option there is the Amazon Simple Storage service. And we'll talk more about the performance of that particular service in an upcoming lesson. We also have archival storage. And we can, using Amazon Glacier, we can either upload data directly to Glacier or use lifecycle rules to transition data automatically from S3 to Amazon Glacier. And so when we think about performance, how the writing data and the retrieval of data, with S3, we have the ability to upload directly and we can do synchronous downloads immediately at will. So we can write something once and then immediately read it. With Glacier, because it's archival storage, once data is written to Glacier, the retrieval process is asynchronous. So, and it generally takes 3 to 5 hours. With standard retrieval, in order to get data out of Glacier, you're going to put in a request and then wait 3 to 5 hours to get that data. Now, you can opt for a faster retrieval in as little less than 10-minute retrieval, but you will pay an additional fee for that, right? So when we think about performance, we have to ask ourselves, what are the access patterns? How will our application access this data? Will it be, write once, read many? Will it be a lot of random I/O or sequential I/O? Or do we need to just simply store this data for long periods of time and we may never access it, right? So those are our options within AWS, and it will help you to be familiar with those options and the nature of each option so that you can determine what will be the most performant data store for a particular scenario. Now let's review the performance of our block store options. So when we deploy applications to EC2 that will use some type of block store volume, whether it's instant store or EBS, SSD, or hard disks, we should be asking ourselves a number of questions. Will our app perform random or sequential I/O? What throughput rates might be required by our application? How frequently will the data be read? How frequently will the data be updated? Will it be a write once, read many type of situation? Or will those particular files be updated constantly? So when we think about log files are generally written once and then perhaps read, several times, if ever. And when we have other things like images or CSS or JavaScript, other types of static content, those might be written once and read many times. We might have database engine files, like when you think of MySQL InnoDB, you have an InnoDB data file that essentially contains the database. And so when you are doing a lot of updates, the actual data in that file is constantly being updated and read. And so when we answer those questions, that will help determine whether we need a random I/O or sequential I/O. So for random I/O, to get the highest degree of IOPS, input-output operations per second, then we could look to instant store volumes. And in some cases, instant store volumes can give us upwards of 300,000 plus IOPS, but with no durability. So that's the trade-off. If you need that data to be both highly performant and durable, then the onus of durability will be on you as a customer, right? So we would have to use some third-party service or software or write our own sort of scripts to automatically, regularly copy that data off to something else that was more durable. And so with EBS, now the trade-off is that we don't get quite the performance as the ephemeral instant store volumes, but we do get some built-in durability, right? And with EBS, the Elastic Block Store, we have, again, the general purpose SSD volumes. Those will give us that persistent storage while balancing price and performance. And so the idea there is, again, that the general purpose SSD volumes will operate at a baseline of 3 IOPS per gig. And so let's say a 400 gig volume would give us about 1,200 IOPS. And for many applications, that might be fine. Now, the general purpose volumes are capable of bursting for some period of time, and they can burst and sustain, a higher level of IOPS so long as they have credits, and they accrue burst credits while they are idle. Now, if we need a consistent, ongoing high performance in terms of our IOPS, we can leverage provisioned IOPS. And so provisioned IOPS SSD volumes give us that guaranteed level of performance, up to 30,000 IOPS. And of course, there is a relationship to the max IOPS volume and the size of the volume. So the larger the volume, the greater the max provisioned IOPS we will be able to provision. Now, if we need more throughput type storage, if we're doing more sequential type of access where we're more concerned about the throughput than we are with random I/O, then we can look to the hard disk volumes. So again, we have the throughput optimized volumes giving us upwards of 500 megs per second for sequential access. And then we also have the cold storage volumes that will give us the absolute lowest cost for infrequently accessed data. Now, a common question here might be, well, if we have data that's infrequently accessed, we already have S3 that can give us low-cost storage for that. And that's true, but one of the benefits to the hard disk cold storage volume over S3 is that because it's a volume attached to EC2, now we can add our own customized security controls on top of that beyond what might be possible with S3. So again, when we think about the performance of our storage, we need to consider all of the options that are available to us and the access patterns. So let's keep in mind that because EBS volumes are independent of the instance, they are connected to the instance over the network. And as a result, some EC2 instances that are not EBS optimized share regular network traffic, such as internet-bound traffic, and EBS traffic are using the same host network interface. So EBS optimized instances provide a dedicated network path specifically for EBS. And that means that the traffic being delivered between the EC2 instance and the EBS volume is not having to compete with other traffic such as internet or inter-instance type of networking traffic. And as a result, we will see better performance between our EC2 instance and our EBS volumes. Now let's review the performance of Amazon S3 buckets. Now we might be using S3 in our architecture, in our infrastructure, for a number of different use cases. We might use S3 for static content. We might use S3 to form a data lake, to store logs, or to store the ingested imports, right? Whatever the case is, if our requests to S3 are typically a mix of different things like get, put, delete, or list objects operations, then how can we ensure the consistent performance for that bucket? How do we avoid receiving slowdown exceptions being returned from the S3 API? The answer to that is to add random hash prefixes to the object keys. So we have to understand that S3 is a distributed system. No one server can handle all of the data that we will store or all of the requests that we will ask of it. And so the data is actually distributed across a number of nodes, and that means that the data is partitioned. And so the key name of our objects will directly influence or dictate which partition that object is stored in. So if we take a look at an example here, we have a list of S3 object names or keys. And so you'll notice here that the pattern is that we're storing things by date, down to the day. And so what we have, depending on the number of objects we're talking about, we could be storing tens of thousands, hundreds of thousands, maybe even millions of records per day. And so in this example, when you have lexicographical sequences, that is alphabetical, including numbers, in order, then that will introduce a performance problem by forcing too much data into too few partitions. We have a lot of data that can only be stored and served by fewer partitions. So ideally, we have that data spread across as many partitions as possible. And we can do that by leveraging random hashes as prefixes to those keys. And so here, you can see we're just adding that random hash to the very beginning. In that case, we could potentially replace the date. We could replace the entire key with a purely random hash if we wanted to. And so again, that random hash will allow our data to be spread evenly across a number of partitions so that no one partition is responsible for any more data than any other partition. And so the thing to keep in mind here is that while random hashes in S3 key names can improve performance, they remove the predictable prefix. And by removing that predictable prefix, it could make searching for objects more difficult. And we will explore that in an upcoming lesson. So keep that in mind when we're thinking about S3 performance. How you name your objects will directly influence the performance of that S3 bucket. Now let's review searching for data in Amazon S3. Like we talked about earlier, when we want to guarantee the performance of a bucket, we can leverage random hashes, or at least random hash prefixes, for our object keys to ensure that we're getting an even distribution across a number of partitions so that we can, again, guarantee performance. But like we've already discussed, doing so would make it more difficult to find items that we're looking for. So if our S3 key prefixes are randomized, how do we find objects? And we also have to keep in mind that the S3 list objects command is not an efficient form of search. That doing an S3 list objects, there's no way of asking S3 really to filter except by the prefix. And we can only do so 1,000 objects at a time. And so the answer here is to store the searchable metadata in an index data store. And in that regard, we have several options. We could store the metadata in DynamoDB and then search based on the primary key or a local or global secondary index. If we wanted more control or more flexibility over the searching, then we could leverage facets or full text searching with Cloud Search or Elasticsearch. And either way, the pattern here is, again, that we're storing the S3 object, or we're storing the large blob of data as an object in S3, and then any metadata that would describe that blob would be stored in something indexed like DynamoDB or Elasticsearch or Cloud Search. And so our application, when our application needs to find something, a particular object or series of objects from S3, it would perform its searches against one of those data stores. That data store would return that key or keys. We could then use that to retrieve that data from S3. Now let's review improving the end user's experience. Now, over the years, numerous studies, including those from Amazon.com, have shown that delays in page load or delaying getting the user what they're looking for will result in lower conversions, which affects our bottom line. So the best thing that we can do for ourselves is to improve the performance for our end users, to get them what they're looking for as quickly as possible. So the question here is, how do we improve the experience of the end user? And one possible answer here is to reduce their latency via caching. And we can do that leveraging Amazon CloudFront. So within CloudFront, we would create a distribution, whether it be a download distribution or a streaming distribution, and then we would configure origins. And so in this example, we're going to serve dynamic content, dynamically rendered HTML or whatever the case may be, or JSON in the case of an API. We will serve that dynamic content from a load balancer. Static content such as images, CSS, JavaScript, PDFs, and so on will be served from S3. So those would be our origins. We can then configure what we call behaviors to say that URL patterns such as JPEGs, CSS, JavaScript will be served from S3, and then everything else would be served from the load balancer. And again, those are behaviors. And then as our users connect to our particular domain or subdomain, they actually connect to an edge location. And they can retrieve that content that has already been cached at that edge location. And by doing that, we lower their latency, which improves their experience by getting them the content faster, and it can reduce the load on our EC2 instances, which could result in our ability to perhaps reduce the number of instances or the size of instances in that fleet. AWS offers a number of database solutions for both relational and non-relational data. In this lesson, we will discuss how the nature of DynamoDB and our data models affect performance, as well as how we can improve performance for write or read-heavy applications. Now let's talk about the performance of Amazon DynamoDB tables. So when we're leveraging DynamoDB within our infrastructure, we should be asking ourselves, how can we improve the performance of our DynamoDB queries? Now, in order to do that, first we need to understand the nature of DynamoDB partitioning and throughput allocation. We would also choose primary keys that would give us an even distribution of storage and request load. Because DynamoDB is a distributed system, our keys, very much like S3, will be distributed across a number of partitions. And what we want to avoid is any one partition being responsible for, the majority or any more storage or requests than other partitions, because that would be a hot partition, and that would lead to performance degradation. We would also leverage both local and global secondary indexes. And then finally, we would use the query versus the scan operation. So remember that DynamoDB is capable of single-digit millisecond response time, but that's only when we use the query operation rather than the scan operation. And as the name suggests, the scan operation is a full table scan. We will not be able to get the absolute best performance by using that scan operation. Remember, again, as I've said before, that tables are partitioned, and within DynamoDB, tables are partitioned according to our throughput capacity and the size of the data that we're storing. So when we look at DynamoDB and how these tables are built, how partitions are built, a single partition can handle 3,000 read capacity units, 1,000 write capacity units, and up to 10 gigabytes worth of storage. So let's say that our table in this example requires 6,000 read capacity units, 400 write capacity units, and initially, or in the short to mid-term at least, we're only looking at about 5 gigs worth of storage. So according to that formula, we would calculate the number of partitions like this. For the capacity, for the throughput capacity, again, one partition can handle 3,000 read capacity units. So we would have 6,000 divided by 3,000. We would then add that to the write capacity units. So one partition could handle 1,000 write capacity units, and we only need 400, so that gives us about 0.4, right? In terms of storage, we only need half a partition. Of course, there's no such thing as a half a partition. And so then the number of partitions will be the greater of those two numbers rounded up. And so the greater of those two would be 2.4, round that up to 3, and that would be the total number of partitions that would be allocated to this table in order to meet the throughput demands that we're asking. And so here we would end up with, again, 3 partitions, and then our total throughput would be allocated evenly across those partitions. And so in this example, each partition then would be allocated or limited to 2,000 read capacity units and 133 write capacity units. Now, the thing to keep in mind is that if any one partition goes beyond more than what it's allotted, then the throughput will be throttled. Even if our total throughput is lower than what we've provisioned in total, again, any one partition going beyond its allotted throughput would result in throttling. So this is exactly why we want to avoid hot keys. Hot keys lead to hot partitions, and hot partitions lead to degraded performance. Now let's talk about primary keys within Amazon DynamoDB. So with Amazon DynamoDB, a primary key can be either a partition key on its own or a partition key plus a sort key, which would be a composite key. Either way, the value of the partition key determines the partition that actually stores and serves the record or item. So let's explore this a little bit. Let's take an example here where, let's say, an e-commerce site such as Amazon.com or others like it displays a product ratings. And members can rate products on a scale of 1 to 5. And members can submit their vote. And we're going to use DynamoDB to collect those votes. And so initially we might think that, the product ID for this table might be a good partition key. But let's explore that. And so by doing that, we might have, product-1 go to one partition, product-15, according to its partition key, would be assigned to another partition, and product 237 to yet another partition. But the issue here is that any particular product that becomes more popular than other products would create a hot key and a hot partition, right? A single product might receive many more ratings than other products, and by doing so it could very well overwhelm the throughput allotted for that partition. Remember what we talked about earlier, that our total provisioned throughput is evenly allocated across the number of partitions. So even if our total consumed throughput is less than our total provisioned throughput, we would still receive a provisioned throughput exceeded exception for any one partition that's going above or beyond the throughput that was allotted to that partition. So how can we improve the performance? How can we mitigate hot keys or hot partitions, right? The best way to handle that is to try a strategy with the values of our primary keys that provides a large number of unique and evenly requested values, but sometimes that's easier said than done. Now for reads, we could easily solve that by leveraging caching with either Elasticache or DynamoDB Accelerator, otherwise known as DAX. Now the benefit to using DAX is that the data model and the API is compatible with DynamoDB. We can leverage DAX without making any changes to the code of our application. With Elasticache, we would have to make changes to our code in order to make our data model and the API calls compatible with either Redis or Memcached. Now for writes, we have a number of options. We could simply buffer that incoming data into either a queue with the simple queue service or with streams in Kinesis. We could also append random values to the key. So in that regard, what we could do is, let's say that for product 1 being, let's say, one of the more popular products. In this example, we could say, let's just append a random suffix from a known range of values. So we say product 1-1, that would go to one partition. Product 1-4 would go to another partition. Product 1-10 would go to yet another partition. But now we need to aggregate all of those. And so again, appending random numbers from that set range forms a different hash, which would therefore spread those requests and spread the storage across those partitions. And so then aggregating would then require 10 requests. So we would make a request for product 1-1, product 1-2, product 1-3, so on and so forth, until we've made 10 requests for product 1-1 through product 1-10. And then we could aggregate all of the ratings for product number 1. So again, just to recap that, it's really important to understand how our primary key, how the nature of our primary key affects performance within DynamoDB when we consider the nature of partitioning within a DynamoDB table. So again, Ideally, a partition key will have a large number of unique values evenly requested so that no one partition is responsible for any more requests or storage than any other partition. And by doing that, that's how we can guarantee that we're getting the most optimal performance out of DynamoDB. Now let's talk about secondary indexes with Amazon DynamoDB. Before we look at the indexes, let's first take a look at an example of maybe creating a movie database within DynamoDB. Now in this example, we're going to use the title of the movie as the partition key because we would have a very large number of unique values, so that because of that value being unique, we can spread this information evenly across partitions. Now in this case, because once this movie data is written, we probably won't update that data very often. New movies will be added, but generally we could expect that this table will have many more reads than we will have writes. It is possible for certain films to be read more than others, so some films would then end up with a hot read, but we could, of course, as we've talked about, mitigate hot reads with caching. Now let's remember what we talked about earlier in terms of querying. The most efficient way to retrieve information from DynamoDB is to use the query operation. And in order to do that, we need an index. In this example, the title or the partition key would be the only thing in this table that is indexed. So if we ever wanted to search based on the year, how could we query against the year across all of the partitions? What if we wanted to query by rating? How would we query against ratings across all of the partitions? For those, we could use secondary indexes. And so here's an example where we're still taking, movie data, but we're putting the relationship between cast members and their roles to a film in a second table. And so in this example, we are using the title of the film as the partition key, and the cast member attribute is being used as the sort key. And that would give us, the partition plus a sort key would give us a composite primary key. Now if we wanted to say, all right, show me all of the cast members for the movie The Matrix, then we could query where partition key equals the matrix and then use the sort key, as the name suggests, to sort based on the cast member name. If we wanted to sort based on some other attribute, then we could create a local secondary index. So a local secondary index allows us to reuse the same partition key, but specify a different sort key. So here we could create a secondary index so that we could sort based on the role. So then we could say, find all movies where film or title equals The Matrix, and sort by role or sort by member. Now, global secondary indexes allow us to use an existing table with the existing data in a currently existing table and specify a new partition key so that we can have a way to perform queries against a new partition key so we can query data across numerous partitions. And so here we might use, create a global secondary index by specifying the year as the partition key and the title as the sort key. And so that way we can query where we could say, find where all movies where the year is 1999 and then sort by the title of the movie. Now, when we're using global secondary indexes, any changes to the table will be reflected in the secondary index, and that will be eventually consistent. Even if we use, there's no option to use strongly consistent reads when we are querying from a global secondary index. They were always eventually consistent reads. Now we could create another global secondary index, in this case using the rating as the partition key and the title as the sort key, so that then we could say find where all movies where the rating is PG-13 and sort by the title. Now, a couple of things I want to point out here. One, the throughput for the global secondary index is provisioned separately and is independent of the table. So we will specify a particular throughput that we need for the table, and we specify the throughput that we would need for our global secondary index. The storage is shared, right? So the storage is being used by the table, but the throughput is different. So our table could have one level of throughput and our global secondary index could have its own level of throughput. I created this example to show you perhaps a bad example of a partition key. Because here, when you look at movie ratings, there are only 5 possible ratings. That means that we will have very few values across perhaps millions of records in this table. And as a result, we would end up with hot keys and hot partitions. We're asking DynamoDB to put a lot of records across very few partitions, right? So a global secondary index like this is probably not the best idea, right? So remember that within Amazon DynamoDB, we have a number of things that contribute to performance. Our choice of our partition key, and once we have a good choice, a good value or pattern of values to use for that partition key, then we can look to improving query performance by leveraging secondary indexes. Local secondary indexes allowing us to specify a different sort key, and global secondary indexes allowing us to specify a new partition and sort key altogether. Now let's talk about improving performance for read-heavy applications. In this example, we have an application leveraging a database instance from the relational database service. And of course, that's deployed with a multi-AZ deployment, RDS giving us a primary and a secondary with synchronous replication across multiple availability zones. So how can we improve the performance when dealing with many read operations? Even if those operations are not constant, even if they only occur during particular windows, we can still improve the performance by leveraging read replicas. With the RDS, it's very easy to create read replicas. We just simply ask for those read replicas, and then RDS will create and manage the replica and ongoing replication. It is worth noting that with most DB engine types, we are limited to 5 replicas per master. With Aurora, that limit goes up to 15 replicas per master, or per DB cluster. Once we have our read replicas, our application will then send read requests to the replica and continue sending write requests to the primary. The primary and our replicas will get different endpoints for that purpose. And by doing this, read replicas will reduce the load on the primary, thereby improving at least reads, potentially both reads and writes. Now, another thing we might ask ourselves in terms of read-heavy applications is how can we improve the performance when dealing with slow queries? Perhaps we've already indexed everything by the book. We've taken a look at our schema and our data model, and we've done all we can to improve the performance of those queries, but just due to the volume of data and the volume of requests, perhaps we still have some queries that are returning slower than we would like. And so for that, we can leverage in-memory caching. To do that, we can leverage Amazon Elasticache, which offers fully managed Redis or Memcached. So the idea here is that we put a cache cluster alongside our application, and the Elasticache can provide the ultra-low latency by keeping that frequently accessed data in memory. So our application would first look to the cache to see if the result set we're looking for is already cached. If it is, we simply return it to the end user with very, very low latency because that result set has already been generated. It's already there in memory. If not, we then retrieve it from the database and then populate the cache. So keep that in mind, that when you're thinking about applications that are read-heavy, we have several options. We have read replicas and in-memory caching, when we could always use both if that particular scenario warrants such an architecture. Now let's review improving the performance for write-heavy applications. In this example, we might be asking ourselves, how can we improve the performance of writes to a small RDS instance? And the answer in this case could be to leverage buffers. In doing so, the performance will be improved by leveraging Amazon Simple Queue Service and decoupled processing with either AWS Lambda or Amazon EC2. Now, in this example, we're leveraging, let's say, a DB T2 small, and that may very well serve an application well, but suffer during occasional spikes in writes. And this is actually a common pattern, that a number of applications could very well be served by a smaller RDS instance. But during those periods where we're seeing a spike in writes, we could have those writes be buffered by a queue. Our application could determine if we're seeing a high volume of spikes, then we could simply write our code to start sending writes to the queue. A simple queue service queue would provide that fully managed, highly scalable way to buffer those incoming writes. And keep in mind that the simple queue service, there's several benefits there. One, there's nothing for us to do in order to make it scalable. It's by default, out of the box, scales to millions of messages per second. It also gives us the first million messages per month are free. Now, we could then leverage AWS Lambda, which would give us, again, that fully managed, highly scalable way of processing messages in the queue. So Lambda could be set to pull messages from the queue and write that data to our database at a pace that our database can keep up with. And by doing that, this very well could improve performance while also saving money as opposed to simply increasing the size of the database. Now, in the case of DynamoDB, we can also use a buffer. So going back to an earlier example where we were collecting product ratings, perhaps we could improve performance by having all of the product ratings. In this example, product 1 sees 4 stars, product 1 sees 3 stars, product 1 sees 5 stars, and so on. All of these writes first go to a buffer. They go to a queue. We could then have a Lambda function pulling those messages out and either submitting those items to the database at a pace that the table can keep up with, or modifying the primary key into a pattern like we saw earlier, where we're appending a random value to the key so that we can get those into the table without creating a hot key or a hot partition, right? So when it comes to write-heavy applications, we have a number of options, and using the simple queue service as a buffer, we could potentially even use Kinesis as a buffer, and those are ways that we can improve the performance for write-heavy applications. AWS offers a number of fully managed and powerful services such as Kinesis, Lambda, the Elastic Container Service, API Gateway, and more. In this lesson, we will look at how event-driven and serverless infrastructures can improve the performance of our applications. Now let's review event-driven architectures. Now, in this example, let's say that we have users who are accessing an API powered by EC2 behind a load balancer, and they are also uploading content and that content needs to be processed and then redelivered back out to other users. So the question here is, how can we improve the performance of file ingestion and processing? We can do that with asynchronous event-driven architectures. And here, the performance can be improved by leveraging Amazon Cognito, Amazon S3, Amazon Simple Queue Service, Amazon Simple Notification Service, and AWS Lambda. So in this particular architecture, we're going to leverage Amazon Cognito user pools, which allows users to authenticate with any OpenID provider, such as Facebook, Google, Amazon.com, and many more. So we're allowing our users to authenticate against a directory that already exists without having to create a new account for them. So they're authenticating against something that can verify their identity, and then we can leverage Cognito triggers to customize that authentication workflow with Lambda functions. Once that authentication workflow has completed, we can then return temporary credentials to the user's client, and those temporary credentials can be used in subsequent requests so that the user's client can communicate directly with AWS services such as S3 or DynamoDB or Lambda or so on. Now in this example, that user will leverage those temporary credentials to upload content directly to S3. And once that content is uploaded, we could then leverage S3 event notifications to a simple notification service topic that can then be distributed to other endpoints. And here we have 3 different queues within the simple queue service. And each queue is subscribed to the same simple notification service topic. And so as that message comes in through the SNS topic, it then gets published into 3 different queues. So now we have 3 copies of the same message in 3 different queues. And this pattern that we're seeing here is called the fan-out pattern. In this example, perhaps we have 3 different operations that need to be performed on the same message. If we were to only use one queue, then the general process of leveraging a queue is to, once an operation has completed, it then deletes the message from the queue. So if we only had one queue, then only one operation would actually complete, and the other 2 operations would never actually see that message. So by leveraging a fan-out pattern, we can have 3 completely different operations performed on the same exact message. And then we can have worker nodes within EC2 that are polling for messages from those queues, performing whatever processing needs to happen with that uploaded data, and then perhaps storing the results. Images, watermarked images, transcoded videos, audio, whatever the case may be, that data can then be stored in another S3 bucket that's configured for, access by our users. Lambda can also respond directly to SNS notifications, and so perhaps in this example, we are also subscribing to the same topic. We're subscribing an AWS Lambda function that as soon as an object is uploaded to S3, Lambda is immediately triggered. Lambda can then pull that metadata about that object, perhaps correlate that metadata with the user ID from the user identity pool, correlate that data with something in a database, and then use Amazon Pinpoint to send a mobile push notification informing them that their file uploaded successfully and is being processed. When the process completes and the output is ready, we could use Pinpoint to send a mobile push notification there as well. So the idea here with event-driven architectures is that there are oftentimes plenty of work that needs to be done, but we don't need to make our end users wait for a synchronous response while that work is being processed. We can process the work in the background, leveraging event notifications to drive that so that our end users can continue doing something else while they wait for that work to be done. Now let's talk about serverless architectures. In this example, very similar to our last example, we have an API and our users are accessing and our users are also uploading content, and we want to leverage event notifications. We want to leverage the ability to perform web identity federation using Amazon Cognito so that users can authenticate against an OpenID provider. But how can we improve the performance of our infrastructure while our team continues to focus on application development? We can leverage serverless architectures. So in this case, the performance can be improved and operational burdens can be handled with Amazon Cognito, Amazon S3, Amazon API Gateway, AWS Lambda, and Amazon DynamoDB. So in this example, instead of running our own API on EC2 and having EC2 instances to manage, we can leverage the API Gateway. It gives us a fully managed, highly configurable REST API. It supports very powerful things like rate limiting, API keys. It supports custom authenticators, transformations. There's a lot of really great things already built into the API Gateway. We could leverage Lambda for the backend. So AWS Lambda functions would then provide that very scalable backend compute platform. There's really nothing for us to do there other than to write code and create Lambda functions. So remember that AWS Lambda, the service, handles all of the underlying compute infrastructure. It handles the deployment of our code and the scaling of our code. If we need 1,000 concurrent executions of a Lambda function, we can do that. And there's really nothing for us to do other than write code. So again, like before, our users would use those temporary credentials received from Cognito to upload directly to S3. We could then subscribe to S3 event notifications with Lambda functions directly. Instead of having queues and instead of having worker nodes on EC2, we could simply have the work being performed by Lambda, and again, removing the need for our team to manage servers. So Lambda in this case could be doing the processing directly. We could, of course, store data in DynamoDB. Remember that DynamoDB gives us a fully managed NoSQL data store with the right primary keys, with the right indexes, and using the query function, we can receive single-digit millisecond latency. Now, another powerful feature of DynamoDB is DynamoDB Streams. DynamoDB Streams allows us to subscribe to the read-only output of the table. So as data comes into the table, as changes are made to that table, new records are inserted, updates happen, deletes happen, those changes come out through the stream in near real time. And we can subscribe to that stream, let's say with Lambda, and you use that stream to analyze the changes in that table or to trigger some other automated process in response to the changes in a table. So again, to recap that, the idea with serverless architectures is that for many teams, we don't necessarily want to be burdened with the management of infrastructure. We want to focus our team on, adding value to our application. And so when that's the case, when you want your team to focus on adding value to your application, developing new features, resolving any issues in the application, then we can offload operational burdens to AWS by leveraging services such as API Gateway, Lambda, DynamoDB, and so on. Based on the security pillar of the well-architected framework, this module will review a number of principles and practices as well as service features in regards to how they improve or potentially weaken the security of our infrastructure, applications, and data. Securing our accounts and credentials and ensuring proper access to resources is a vital first step in securing our infrastructure, applications, and data. In this lesson, we will review identity and access management and discuss options we can leverage to create a more secure environment. Now let's discuss design principles as they relate to identity and access management. When we think about identity and access management, the design principles that we should keep in mind are that we are wanting to create a strong identity foundation. And we can do that by leveraging the principle of least privilege. Not everyone needs to be an admin member, right? Not everyone should be an admin member. Members of your team should have the permission to do what they need to do and not necessarily any more. Components within your infrastructure, such as EC2 instances or Lambda functions, should have the permissions they need to do their jobs, not necessarily any more. We should also enforce separation of duties, and we should reduce or eliminate the need for long-term credentials. So remember that within the Identity and Access Management service, we have the ability to create roles. And roles are a very powerful and effective way of allowing us to delegate permissions to other Amazon services, such as Lambda or Elastic Beanstalk, or to an EC2 instance, or to another account. And so instead of relying on long-term credentials being embedded in our code, instead of sharing long-term credentials, we can rely on roles to grant temporary credentials. And so that if those credentials were somehow compromised, we know that they will expire. So as we move forward through identity and access management, let's keep these design principles in mind. Now let's talk about securing identities and credentials. So with the Identity and Access Management service, this is responsible for authentication and authorization of our users for accessing AWS resources. We can create users, we can organize those users into groups, we can set a password policy and enforce, a certain type of password to be created. We can also enable multi-factor authentication. And remember that the management and configuration of these things is our responsibility. Any of the credentials that we create here, it is the responsibility of our organization and our users to protect those credentials. And those credentials come in different forms. We have access keys, which is a pair of the access ID plus the secret key, and those are used to access the AWS API. You could access it with the CLI tools, with the SDKs, and those credentials, the access key and secret keys, are considered long-term credentials. We can also give our users the ability to log into the management console by granting them a username and a password. Now, it's worth noting that when they log into the management console actually makes use of the API in the background. The management console does not have any kind of special hook that bypasses the API. And so all of these would be long-term credentials that, again, are our responsibility to create and manage and secure and follow those design principles that we talked about earlier. And so as far as our users, right, we can use the Identity and Access Management service to create users, and those are created, they exist within the IAM service. Like we've talked about, we can give them the ability to log into the management console. Each person can create and manage their own access keys. We can create policies that allow them to create their own access keys, but also prevent them from interfering with someone else's. And of course, they can use those long-term access keys to configure their local tools for the CLI or SDK so that they can develop locally. We can also enable an MFA device per user. We have similar controls with policies that we can use so that each user can configure their own MFA device and not interfere with someone else's. We can organize our users into groups. Perhaps Mr. Lebowski and Mr. Sobchak are developers, and Mr. Quintana is a DBA, right? So again, like we talked about in those design principles, we should be following the principle of least privilege, ensuring that our users have enough permissions to do their jobs, but not enough to step on other people's toes, right? So if a user needs more permissions than what they currently have, then we should be following a change management process showing that they have explicitly requested that increase in permission, and that we can then show that they have a legitimate use case for needing that increase in authorization. Remember that we have a number of different credential types. If you find yourself logging into the AWS Management Console with an email address and a password, you are logging into the master account, which has root access. And we're going to talk about that a little bit more here coming up. If you're logging in with simply a username and a password, then you're logging into the AWS Web Management Console as an IAM user rather than the master account. And then we have access keys and secret keys that are used to configure the CLI tools or the SDKs. We also have temporary credentials that we'll talk about later on as well. So just to recap that, in terms of identities, in terms of credentials, remember that within the shared responsibility model, as a customer, it is our responsibility to configure our users and their permissions appropriately. It is our responsibility to protect those credentials, whether it be the master account credentials or the credentials for a particular IAM user. All of those things are our responsibility. Now let's talk about securing access to resources. Remember that the way that we grant access to resources is through policies. Policies grant authorization to perform actions on resources within our AWS account. They are written in JSON, and we have two types of policies. We have managed policies, which are first-class objects that we can create and apply to multiple entities, such as users, groups, roles, and so on. So within managed policies, we have the policies that are created and managed by AWS. AWS gives us a long list of pre-made policies to choose from. And of course, we can create our own customer-managed policies. And again, the difference between managed policies and inline policies is that a managed policy is a first-class object. It exists on its own and can be applied to numerous entities. An inline policy does not exist on its own. It exists as an intrinsic part of a user, a group, or a role. And generally, we use an inline policy when we want to write something very specific that only applies to that one entity. Now, we can create policies in a number of different ways. We can create them using the policy generator within the AWS Management Console. We could also write them by hand. I don't recommend starting a policy from scratch by writing it by hand, simply because JSON has a fair amount of syntax, and it's very easy to miss a curly brace, a quote, or a colon, or so on. And so what I generally do is I will start with the generator and then modify the policy by hand once the generator has given me the initial JSON to start with. Now, the evaluation logic, it's important to know and be very familiar with how policies are evaluated. The evaluation logic says that, remember that for any entity, we can apply multiple policies, and any one policy can have multiple statements. And so when the permissions are evaluated, the IAM service will put all of those statements across all of those policies together into one long list. And we first look for an explicit deny. If we don't find an explicit deny in that list, we then look for an explicit allow. And if we don't find an explicit allow, we then fall back to the default implicit deny. So it's a security-first approach. In order for a user to be able to perform that action on that resource, they have to be not only allowed, but they also have to be not explicitly denied, right? And so there's a common question, well, if we have to explicitly allow, why would we ever explicitly deny? And the answer to that is that by using explicit denies, we can create further guardrails around the permissions that our users have. So now let's take a look at an example policy. In this policy, first, let's take a look at the version. It's important to understand that the version here is not our version. This is the version of the policy language, the DSL, the domain-specific language with which the policies are written. So we pull this value. It's a date-based version that represents Amazon's version of the policy language, and we can pull that from the documentation. Next, we have the statement. Now, even though it's a singular word there, statement is actually a collection of statements. So remember that one policy can have multiple statements. It's a list of the permissions being granted by this policy. From here, we're then going to explicitly state the effect of this statement, whether to allow or deny. In this case, we are allowing the following actions. In this case, we're going to specifically allow the S3 get object and S3 put object actions. And you'll notice here that those actions are namespaced according to the name of the service, in this case S3. And then we list the resources. We are explicitly saying that we are allowing these actions on these resources. Resource is a list. In this case, we're saying that we are allowing the get object and put object actions on any object in this bucket. You'll notice here it says my bucket /star. So the /star here means that we are applying those permissions to every object in the bucket, not the bucket itself. Now, here's an example of a policy with conditions. Again, here we're going to allow this particular set of actions under the condition that the request was made from a particular set of IP addresses, perhaps IP addresses that belong to our corporate static range, right? So conditions provide much more granular control over when or from where or under what conditions that the request is actually allowed or denied. So we have a number of different things to choose from within conditions. In this example, we're using the IP address, the source IP. Right? So here again, we're saying that under the condition that this is allowed, under the condition that the source IP address comes from a very particular range. Another example here says that if under the condition that the server-side encryption header is not set or does not equal AES 256, we will then deny the request. Right? So it might be allowed. We saw this in an earlier example of a policy that we were allowing it in one policy, but here we're saying if we are not setting the server-side encryption flag, then let's actually deny the request. So here's an example of a policy that will enforce server-side encryption on that particular S3 bucket. So you can see that conditions give us a lot of room to further control and create very fine-grained permissions with our policies. Now, another thing that we can do is to leverage policy variables. You'll notice here highlighted in yellow, we have a policy variable, and we spell that out with $, curly brace, AWS : username. Right? So policy variables allow us to generalize policies rather than having to write many specific policies. So this particular policy applied to a group of users would allow each user in that group to manage their own access keys. You'll notice the asterisk there, IAM asterisk access key asterisk. So it allows them to create, manage, delete, and so on. It also allows each user to change their own password because the resource contains that policy variable. And so the variable will be replaced by their actual username at the time the policy is evaluated during the actual request. And so it allows us to write one policy that can be applied to multiple users rather than in a specific policy for each user. So to recap that, let's keep in mind that the creation of these policies, the specification of permissions and conditions, allows and denies, all of this is our responsibility. Under the shared responsibility model, it is our responsibility to create the appropriate permissions for our users, for our roles and groups. It is Amazon's responsibility to faithfully execute those permissions. So keep that in mind, that within policies we have a lot of room to create very granular controls and keep our resources secure. Now let's talk about temporary credentials. Before we actually talk about temporary credentials, let's first talk about credential anti-patterns. There are just certain things that we don't want to do in regards to credentials. And of course, managing credentials is our responsibility. So one thing would be we don't want to embed access keys in our code. There is a security issue there. They could be exposed. Developers could find them and perhaps just copy and paste and use them in ways they weren't intended. Or now we have a logistical issue in that we have to rebuild, retest, and redeploy when we want to switch out credentials and rotate our credentials. So we also don't want to embed them in environment variables for all the same reasons, right? They could be exposed. Now there's a logistical issue, right? Who has access to that machine? We don't want to share credentials with third parties. We don't want to share credentials, a single set of credentials with potentially hundreds of enterprise users. We certainly don't want to share credentials with millions of web or application users, right? So we don't want to have to embed credentials in a mobile application and then allowing, millions of users to leverage that same set of credentials and then make it very difficult for us to rotate those credentials by creating and deploying a new version of the mobile application. And the way that we can get around that is to leverage temporary credentials. And we can leverage temporary credentials by using roles. And we'll talk about how roles work here in an upcoming lesson. Now, the better practice here is to delegate permissions to, let's say, EC2 instances. When we have applications running on EC2, instead of embedding credentials within the application, we can simply allow the application, using the SDK, to receive temporary credentials from that instance with a role. We can delegate permissions to an AWS service, such as Elastic Beanstalk, and allow the Elastic Beanstalk service to perform actions on our behalf. We can delegate permissions to a user temporarily. So we could follow sort of a pseudo pattern with our accounts, in that perhaps some users generally through most of the day have a particular set of permissions, but perhaps in some cases they need to temporarily elevate their privileges. And so they can leverage a role. They can assume a role, get temporary credentials, and then use those credentials to perform some action that they are normally not able to do. We could also delegate permissions to a separate account, and that account could be one that you own, which is a very common practice, right? You could have an administrative account where all of your users are, and then perhaps you have an account per department, per environment, or whatever, and your users exist in one place, and you leverage roles to assume into those other accounts. That other account could be a third party, such as a vendor or a client. So again, just as a reminder, it's so important, and I think it's worth mentioning several times, is that in the shared responsibility model, The creation and the management of these things is our responsibility. So we should take them seriously and really look at how we are leveraging credentials within AWS to provide, a secure access to our resources. Now let's review roles for EC2. In this example, we have an application running on EC2, and it needs to authenticate to the AWS API so that it can access other Amazon services such as S3, DynamoDB, Kinesis, Simple Queue Service, and so on. In order to do that, it needs credentials. Now, in order to get those credentials, we can apply a role to the instance, and that gives that instance a way of retrieving temporary credentials. We then apply a policy to the role, and the policy, as we've talked about earlier, specifies the actions that are allowed to be performed and the resources on which those actions are allowed. Now, the security token service is the service responsible for generating temporary credentials. So the security token service will generate those temporary credentials and then deliver them to the hypervisor, or the hypervisor more accurately will go and fetch them from the security token service. And then the AWS SDK or the CLI tools, if they don't find credentials embedded somewhere, they will automatically look to the instance metadata service. So remember that the instance metadata service is available to all EC2 instances. It's a small HTTP-based service that we can make calls to get information about that EC2 instance. In this case, our application should not have any kinds of credentials embedded within it or within environment variables. And so as a result, the SDK will not find them and then will automatically make a call to the instance metadata service to retrieve those temporary credentials that were put there by the hypervisor. Then our application can use those temporary credentials to authenticate to other AWS services. And so the beautiful thing about this is that now we've given our EC2 instance and our application a way of retrieving credentials that are regularly rotated. These credentials live for some short period of time, and they are automatically rotated 5 minutes prior to expiration. And so if those credentials were somehow compromised, we don't have to worry about them so much because we know that they will expire very quickly. And so that allows us to stop embedding credentials within our code, within environment variables, or within some type of a configuration file that's deployed alongside of our application. Now let's talk about cross-account access. Here in this example, we have two accounts. We have our admin account on the left, and we have our production account on the right. And this is a very common pattern within AWS. So the idea here is that we have a user that exists within the admin account, and we have resources existing in some other account that that user needs access to. The way that we can enable that is through roles, cross-account roles. So here, we're going to create a cross-account role that, again, provides that secure way to allow access to resources in that account from another account. When we create that role, we are establishing what we call a trust relationship, and that tells AWS that the production account is trusting or delegating permission to our admin account. We then apply a policy to the admin role. Again, the policy will define the actions and resources that are allowed by the use of that role. On the admin account, the only permission we have to grant Mr. Hofstadter user is the ability to assume the role. So we are allowing the STS assume role action, and that is that critical permission. So without that, the user would not actually be able to leverage that role. Then our user would make a call to the security token service to say, I want to assume this role. The security token service would then return temporary credentials, and our user could then use those temporary credentials to access resources in that other account. Now that process of assuming that role and collecting those temporary credentials and making those temporary credentials available for use in subsequent requests, that whole process can be simplified using the SDKs and the CLI tools. We have ways of configuring those tools to automatically go and fetch those temporary credentials by specifying different profiles. So we could say that our normal work just uses our standard credentials, but if we wanted to leverage a different profile, say in this case the production profile, then the CLI or the SDKs can automatically go and get those temporary credentials and use them for those calls. Right? So again, keep in mind that a very common pattern, and one that is very worth adopting for the sake of isolation between accounts, instead of having multiple users per account, we have one place where our users exist and one place to manage our users. And by leveraging cross-account roles, we can gain secure access to those other accounts. And this could be accounts that you own, or it could be a vendor-client relationship as well. So if you ever hire, a consultant, someone like myself, for example, then there's no need to create a new account for us. We already have our own account. So all you need to do is grant us the ability to assume or give us a role that we can assume, and by using that role, we already would have secure access into that account. Now let's review federated users. For any organization looking to leverage AWS, you might be thinking, well, I already have a number of organizational users. I have directories such as LDAP or Microsoft Active Directory. Perhaps we have web and mobile application users who log in with Facebook or Google or some other OpenID provider, and we want to grant them access to AWS resources. And so the question becomes, how can we allow users to authenticate with existing credentials and access AWS resources? How can we avoid duplicating user accounts? And the answer to that is to leverage identity providers. Within AWS, we have a number of options for identity providers that will allow our users, wherever they are, to authenticate with their existing accounts so that we can manage accounts centrally and grant those users temporary access to AWS resources. So these options would be, first, SAML. Using the SAML 2.0, we can grant access to the AWS Management Console, to the CLI tools, to direct API access for users authenticating with existing enterprise credentials. We also have the AWS Directory Service, which would allow access to the AWS Management Console for users authenticating with Active Directory username and password. So the AWS Directory Service is ideal if your work is generally focused around the Management Console. If your employees, team members need more lower-level access using the CLI or direct API access, then you would probably want to look to SAML. We also have Amazon Cognito. So Amazon Cognito can provide API access for web and mobile application users who are authenticating with existing OpenID Connect providers such as login with Facebook, login with Google, Twitter, and so on. Then we also have AWS Single Sign-On. Single Sign-On provides access to multiple AWS accounts and business applications. It has built-in SAML integration with business applications such as Salesforce and Office 365. So It's a very common practice within AWS to leverage multiple accounts, and we can use AWS organizations to manage those accounts. And so the AWS single sign-on service allows us to integrate existing credentials that can then be used to access multiple AWS accounts. So as you can see, we have a number of options to satisfy our federation needs. And so if you do have a large team that needs access to AWS, there's absolutely no reason to duplicate those accounts. We can leave those accounts wherever they are and leverage one of these tools to provide that seamless, very straightforward way of gaining temporary credentials in order to access AWS resources. Now let's talk about IAM best practices. First, with our new accounts, there are some first steps, very critical first steps that we should take. So if you've just recently signed up and you are still logging in with an email and a password, there are some things that we need to take care of. One, we should enable CloudTrail, because CloudTrail, remember, is the service that records all the API calls made to the AWS API. So by enabling CloudTrail first, that will then record and leave an explicit log of everything we do after that. Then we should create an admin user, perhaps a super admin user as an IAM user. Now you could then add an optional condition. Remember earlier we talked about conditions so that we could further contain, say from where or what time that user is allowed to log in, or actually use those permissions. So you could create an admin user, but perhaps they're only allowed to use that account from on premises. We should then enable multi-factor authentication on the root account. Remember that the root account has absolute access to everything all the time, and the access cannot be limited. We'll talk more about that here in just a minute. We should then enable cost and usage reports, because that's one of the things that generally needs to be done with the root account. And then we should log out of that root account and then log back in as that admin user. Once our new accounts have been cleaned up and secured in this way, we can then go on with that admin user to create additional users, groups, and so on. Some other best practices to keep in mind with identity and access management is to remember that the master account, those root credentials, if you're logging in with an email address and a password, then you are accessing the master account. We should protect that account at all costs. So our master account has, root privileges that cannot be limited. If someone compromises the master account, they could perform any number of attacks against your account. They could spin up expensive resources that you would have to pay for, or they could delete resources that you would have to pay for in other ways. We should then, for the master account, we should delete any existing access and secret keys because they will not be used. Leaving them there only increases the surface area of an attack, right? We should not be using our master account for day-to-day operations. We should only log into the master account on those rare occasions where we perhaps need to do something with billing or the few other things that require the master account. Again, as we've talked about before, we should be following the principle of least privilege, giving our users and our roles, our EC2 instances and applications enough permissions to do what they need to do and no more. And of course, we should rotate long-term credentials. If our users have access keys and passwords, those should be rotated regularly. And then lastly, for anyone who logs into the console, especially the master account, we should enable multi-factor authentication. And remember that within IAM policies, we can enforce multi-factor authentication with conditions. So we could say that certain operations are only allowed when a multi-factor authentication PIN or authentication is present. So by following these best practices, we can continue to ensure that our AWS resources are kept secure. Detective controls are another key ingredient to a secure environment. With AWS, we have an easy ability to monitor every aspect of our infrastructure and create an environment in which nothing goes unnoticed or unrecorded. In this lesson, we will review features, options, and practices as they relate to monitoring our infrastructure and applications. Now let's review design principles as they relate to detection and monitoring. Now, the design principle that I want to talk about here in terms of detection, detective controls, is to enable traceability. The idea here is that we want to leverage real-time monitoring, auditing, and alerting with logs and system metrics so that we can automatically respond to abnormal behavior or changes to our environment. Now, the major premise here is that we can leverage managed services such as Amazon CloudWatch, Amazon CloudWatch Logs, AWS CloudTrail, and so on, Simple Notification Service, and others, so that we as an organization don't have to build, manage, and scale the monitoring and logging service ourselves. We can focus on application development while allowing AWS to handle the operational burdens of the monitoring back end. Now let's talk about monitoring our infrastructure. Any given infrastructure needs to be monitored not only so that we're aware of performance or whether or not there's an outage, but also so that we can determine whether there's a security event. So in the beginning, it's important to establish a baseline of normal behavior so that you can then later identify abnormal behavior. And of course, the only way to do that is through regular real-time monitoring. For example, a rapid spike in the load balancer error statuses may indicate a security event. A rapid spike in CPU, disk, or network I/O may also indicate a security event. We can use CloudWatch alarms to then trigger notifications or automated responses to deal or investigate with security events that we might detect with our monitoring. Now, those are just a couple of examples of attacks that come through our infrastructure, but there are other attacks that are designed to change our infrastructure, and we want to watch out for those as well. And we can use AWS Config, which provides continuous monitoring of resource inventory and the current configuration. We can create config rules that represent a desired configuration of resources at a particular time. And so that if config notices a change, if it detects a change to our infrastructure that violates our current configuration, it can then send a notification to us or to a Lambda function that could then be used to potentially reverse those changes, right? So again, automated procedures can be run by Lambda in response to events, either notifying us or automatically rolling those changes back. So for example, we might have a security group that is defined by a rule to say that it should never allow port 22. And if someone inadvertently, through accident or malicious intent, adds port 22, config could see that, trigger Lambda, and Lambda could then undo that change. Those notifications could also be sent to other workflow systems that would allow, routing, escalation, and event management, right? So by monitoring our infrastructure, again, not only for performance and availability, but also for security, we can create a much more resilient, reliable, and secure environment. And all of this is leveraging managed services. The monitoring here itself is being managed by AWS rather than our team having to carry the burden of managing and scaling the monitoring back end. Now let's talk about capturing logs. Before we talk about the technologies we can use to actually ingest and capture logs, let's first review where logs can come from. Logs can come from elastic load balancers, generating access logs. Logs can come from our applications or operating systems running on EC2 or in containers with the Elastic Container Service. Logs can be generated by Lambda. Whether or not our code is actually writing any logging output, the Lambda service will generate logs anyway. We also have S3 access logs. We have VPC flow logs as well, allowing us to capture metadata about the traffic passing through our VPC, whether or not packets are accepted or rejected, source and destination information. We also have CloudFront access logs. And then, of course, we have CloudTrail logs. Remember that AWS CloudTrail is a service that records all of the calls, requests made to the AWS API for the purpose of managing AWS resources. So anytime credentials are used to manage a resource, we can capture the fact that, which credentials were used by leveraging CloudTrail. And of course, this is not an exhaustive list. It's just an example of where we might find commonly used logs. Now, when it comes to capturing those logs, we have a number of choices. So Elastic Load Balancer logs can be stored in S3. Our application could leverage the SDKs to write to CloudWatch logs directly, or they could simply write to a file on the local EC2 instance and allow the CloudWatch logs agent to stream those logs to CloudWatch log service. VPC flow logs are automatically sent. By enabling those, they are automatically sent to the CloudWatch log service and again contain metadata about our network packets flowing through our VPC. Lambda logs by default are streamed to CloudWatch logs, and of course that's a required thing in order for us to be able to actually create a Lambda function and invoke that Lambda function. The Lambda needs an execution role that allows it to write to CloudWatch logs. CloudFront access logs can also be stored in S3. And CloudFront access logs gives us a way of seeing exactly the kinds of patterns of access that are happening through our CloudFront distributions. And now it's a common practice that if we are using S3 as an origin, then you would probably want to enforce access to that content in S3 through CloudFront so that your CloudFront access logs are accurate. We also have CloudTrail events. Now, CloudTrail could record logs directly to S3, or we could stream CloudTrail events through CloudWatch logs and get more real-time access to events taking place within our infrastructure. We can also capture Route 53 DNS queries. Those can be streamed to CloudWatch logs so that we can get a near real-time insight into which domains are being requested from Route 53. And then, of course, a lot of these logs could very well go to S3. Whether the logs are collected in S3 directly or if they're collected in CloudWatch, CloudWatch could then send them to S3. And then after some period of time, we might decide that due to regulatory compliance reasons or legal reasons, we may need to keep those logs even if we might not look at them again. And so remember that we can leverage lifecycle rules within S3 to automatically transition those logs to Glacier in order to lower our cost of storage for the long term, right? So logging is a key component of securing our infrastructure. We ideally want to log everything. Logging can help us with security. It can help us create, and capture a data that we can then analyze and use to track trends and user behavior. And so it's important to understand where logs are generated and the options we have for collecting and storing those logs for the long term. Now let's review analyzing logs. Within AWS, we have a number of options that we can use to derive meaning from our logs. So we've talked about already where logs come from. We've talked about how we can capture those logs. And so here, we're going to review a number of options we have in terms of analyzing those logs. So first, we have CloudWatch alarms and filters. So we can use CloudWatch filters to derive custom metrics from those logs. And then from there, we can create alarms. AWS Lambda can process log events directly, and we can use Lambda to programmatically look for patterns that warrant some type of a response. We can leverage AWS Simple Notification Service, and with SNS topics, we can send a notification which can allow integration with some third-party services. Those notifications can and should be included in your workflow with tools such as collaboration or incident response services, right? So plenty of organizations out there today are using tools like Slack in order to collaborate with team members in real time, so that by having notifications be put directly into that tool, into a workflow that humans are already looking at, then it becomes much easier for us to be aware of what's happening within our infrastructure. And so as far as security and incident response goes, even if the response is entirely automated, at least humans are seeing that something is happening. And so if we see that something has happened, that the response has started, then we might want to make note that we're also looking to see if it's going to finish or if it was automatically resolved. And if not, then we could step in and take action. We also have CloudWatch subscriptions. CloudWatch subscriptions can send logs in near real time to a number of services such as Kinesis or Elasticsearch. And from there, AWS Lambda can process data from Kinesis. Again, in near real time, as the data is streaming in, we are using Lambda to pull from Kinesis and derive meaning and value out of those log events. And perhaps we store those results in some database such as DynamoDB. For example, if we wanted to create, some type of a real-time dashboard related to the health or status of our systems or user behavior, whatever the case may be. Amazon Elasticsearch Service can also subscribe to CloudWatch logs streams in near real time. An Elasticsearch Service includes Kibana, which is a very powerful UI that allows teams to visualize and analyze logs. CloudWatch can also automatically archive logs directly to S3, and now we have a central place for numerous other services to access those logs. From there, we could use Amazon EMR to do any number of advanced big data operations. In the very least, we could transform those log files into, say, Redshift load files. We also have Amazon Athena, which provides a serverless platform for querying data directly in S3. It doesn't need to be extracted, transformed, and loaded into anything else. We can perform SQL-based queries directly on the data as it exists within S3. And then, of course, we can have business intelligence applications connect to Redshift or Athena with existing ODBC and JDBC drivers and run any ad hoc query they can think of. And lastly, we have a number of third-party services such as Splunk or Loggly that we can grant read access to our S3 buckets, and those services can pull log data directly from S3 and give us, some proprietary means of analyzing data. Right? So as you can see, we have a number of options in ways that we can analyze logs within AWS. And all of this together can help us build a more monitored and secure environment. For applications running on EC2, security begins with the network and our operating system. In this lesson, we will look at principles and techniques that can guide us to securing our infrastructure most effectively. Now let's review the design principles as they relate to securing our infrastructure. The design principles here says to apply security in layers. And what we mean by that is when we think about our VPC and our network, we have a number of layers, starting with routing. Routing is our first line of defense. Packets that can't get anywhere, packets that have no channel through which to flow, aren't dangerous. So routing is our first line of defense. Remember that with routing, we can control which parts of our VPC can communicate with other networks, such as the internet or a VPN. And in doing so, we can whitelist certain ranges. Once traffic is flowing, we then have network access control lists. So network access control lists would be the next layer, providing a firewall for the subnet as a whole. And now, once traffic is routed, we can then start to filter that traffic based on source, destination, ports, and protocols. We then have security groups as the next layer. Security groups apply to individual instances or database instances, Elasticache, and elastic load balancers. Those are the layers that are provided directly by Amazon VPC. And we also have layers within the operating system itself. So within the operating system, we can also leverage, OS-based firewalls, intrusion detection systems, and intrusion prevention systems as well. And so the idea here is that we don't want to apply or rely on security at just one external boundary, but rather we should be applying security at key internal boundaries as well. Now let's review routing as security. First, routing, just to be clear before we get to the details of it, routing is concerned with whether or not traffic is allowed to flow, period, from one network to another network. And so we do need to keep in mind that every VPC comes with a default route table, and we can create custom route tables. Now, by default, the default route table is also set as the main route table. There's a difference between the default route table and the main route table. You can choose any route table to be the main route table. And so, with no explicit association to a route table, a subnet will default to being implicitly associated with the main route table. So that's what we're seeing here in this example, is that this particular subnet has no explicit association. Therefore, it is implicitly associated with the default route table, which has been selected as the main route table. Now, it's also worth noting that every route table includes what we call the default route. And the default route is included there to ensure that local traffic remains local. You'll notice here that that route is 10.2.0.0/16, which is the range of our VPC. So every route table includes that local route. Now, in order to gain access to the internet, we need to create route tables and routes in order to make that happen. First, we do have an internet gateway which is attached to the VPC. We then have a route table which is explicitly associated with the subnets that we want to control with that route table. We then have a route added to our route table that says IP ranges other than local are then routed to the internet gateway. And of course, you'll also notice here that within that subnet, we are allowing our EC2 instances to be automatically assigned a public IP address. In order for instances inside this subnet to communicate with the internet, they would need a public IP address. And once they have that, then traffic, according to this route table, traffic between this subnet and the internet would be allowed to flow through the internet gateway. Now, it's also worth noting here that, again, getting back to our point about routing as security, this is where it happens. We can, instead of listing all zeros, which would mean any and all addresses, we could whitelist specific ranges. If we wanted our instances to communicate over the internet to a known group of hosts, such as a trusted third party or our corporate static range, then we could whitelist those and allow communication with trusted systems. Any other traffic outside of that range would not be allowed to flow. Now, it's a very common practice that in any given architecture, we have some instances, such as backend instances, that need to reach the internet while remaining private. These backend instances may need to reach the internet in order to download code updates or patches. They may need to call out to configuration management or some third-party logging server. And so we want them to be able to do that, but we don't want hosts that are on the internet to reach in. And so we can keep them private with network address translation. And so we can leverage the NAT gateway that will give us that fully managed network address translation essentially as a service, this device being fully managed by AWS. And then leveraging our route tables, we can route internet-destined traffic to the NAT gateway. And by doing that, we allow our private instances to reach the internet while keeping them protected from the internet. So the pattern that I hope you're starting to see is that routing is concerned about whether or not two different networks are allowed to communicate. Routing is not at all concerned with protocols and ports. It's only concerned with whether or not this range of IP addresses is allowed to communicate with some other range of IP addresses that are a part of two different networks, regardless of ports and protocols. Once we have a channel by way of routing, then we can start to filter the traffic. And we'll look at those mechanisms in upcoming lessons. But for now, so we've talked about routing to the internet, we've talked about routing with network address translation. So now let's talk about routing between two VPCs with VPC peering. With VPC peering, we would first need a peering connection. The peering connection provides that communications channel between two VPCs. Now, that connection is fully managed by AWS. It is not a single point of failure. It is not a network bottleneck. Right? So as far as the communication, the reliability, the resilience of that connection, we don't have to worry about it. It's all fully managed. And the way that we enable traffic to flow, we first have to create the peering connection, and then we create the routing rules. So you'll notice here that each route table contains their local routes, and they also contain a route, sort of a complementary route, where each VPC is pointing toward the other by way of the peering connection. And so again, routing is our first layer of security. When it comes to allowing internet access, like we mentioned before, we can choose to whitelist certain ranges so that our systems can only communicate with trusted providers or hosts out there on the internet. In terms of peering connections, we could choose to route the entire VPC, or we could choose to route only certain subnets. So we have a lot of control over how traffic actually flows between any two networks. Now let's talk about network access control lists. Here in this example, we have a load balancer in a public subnet, and we have application servers in a private subnet. Now, the reason that we have them separated like this is because they are different functional tiers. And then when we have different functional tiers, they will each have their own port requirements. So the load balancer will need certain ports open. Our application tier and database tiers will need certain ports to be open. And so we can tailor the firewalls for those different functional tiers by placing them into different subnets and applying unique network access control lists to each subnet. So here for our public subnet, we will create a network access control list specific for that tier. Now the ingress rules for that would look something like this. You'll notice here that in order for a network access control list to work, we have to specify both ingress and egress rules. For our ingress rules, we're specifying the first two rules would be 80 and 443. You'll notice that we're specifying the protocol as TCP rather than UDP or something else. The source, you'll notice, is all zeros. That means that the requests on those ports can come from anywhere, including the open internet. And so by setting those two rules, we now allow those ports to come into the subnet, right? So the firewall, the network access control list, is the firewall for the subnet. We have now allowed those two ports to come in through that firewall. And now any other port, such as port 22, would be denied before it was ever even evaluated by a security group, right? Because it's being denied by the subnet firewall, by the NACL, it doesn't even have a chance to reach the security groups of our devices. Now we'll come back to rule number 120 here in just a moment, but first let's take a look at egress rules. Now you'll notice here that we're specifying TCP ports 1024 through 65535. And so when we think about the nature of request and response, the load balancer is receiving requests on port 80 or 443. It will then send a response on an ephemeral port, a random ephemeral port. And if you look at the documentation, you will find that the elastic load balancers and NAT gateways use a very wide range for ephemeral ports, 1024 through 65535. And so in order for that random ephemeral port to leave the subnet, we have to allow that in our egress rules. And so now any other ports less than 1024, such as port 22, port 53, and so on, would be denied. So if anything inside that public subnet were to try to communicate with the outside world using any other protocol or any port less than 1024, those requests or those packets would simply be dropped. They would be denied. So now our load balancer will receive a request on 80 or 443. It will forward that request. In this example, it will forward that request to our backend on, say, port 8080. It's a common practice to have our backend instances listen on a non-privileged port. And so if our backend is listening on, say, port 8080, then that would actually be covered, that port would be covered by the rule number 100 in our egress rules. And so our backend instances will listen on port 8080. They would then send a response back to the load balancer on an ephemeral port. And so that's what justifies the need for this rule number 120. We need to allow ephemeral ports to enter our public subnet, but you'll notice here that we're specifying for the source, we're specifying 10.2.0.0/16, which is the same range as our VPC. We don't want ephemeral ports entering our public subnet coming in from the internet. We only want those ephemeral ports coming in from our VPC. All right, so now let's take a look at network access control lists for our private subnets. You'll notice here that we have a VPN connection between our VPC and our on-premises data center. So now we have different ports to tailor for our private subnets, for our application tier. So again, we apply a unique network access control list to that private subnet, and we specify ingress rules that are specific to the needs of that tier. In this case, we're going to allow port 8080, but you'll notice the source as 10.2.0.0/16. So our backend instances are listening on port 8080, but we only want that port to come in if it originated from our VPC, right? We don't want port 8080 coming in from the internet. We only want it coming in if it originated from our VPC, which is where our load balancer is. Then, of course, our load balancer can send its requests to our backend on port 8080. You'll also notice here that we're allowing port 22 to enter, but only if it originates from our corporate data center, right? We don't want port 22 coming in from the internet. We only want it to come in as long as it comes across our VPN connection. And so port 22 coming from anywhere else will be denied by the network access control list. Again, before it ever even gets a chance to be evaluated by a security group. In fact, the security group will never actually see that packet because it was dropped before it ever got inside the subnet. Now, in order for responses to leave the subnet, we need egress rules. And again, you'll notice here that we're specifying those ephemeral port ranges, 1024 through 65535, because those are the ports that our responses will leave on, right? And so our backend instance is receiving on port 8080. It then sends a response on a random ephemeral port, and those ports, according to rule number 100 in our egress rules, those ports would be allowed. And anything else, any port less than 1024 would be denied. So if our application servers were compromised somehow and an attacker tried to send data out on port 22 or port 80 or 443, then those requests would be denied by the network access control list. So to summarize network access control lists, we could describe them as a firewall for the subnet and for the subnet as a whole. Regardless of what instances are inside that subnet, regardless of how many instances or what security groups they use, the network access control list is a firewall for the subnet. They are stateless. What that means is that a network access control list does not recognize responses as being responses. And so that means that we must specify both ingress and egress traffic. And we do have the ability to specify allow or deny rules. Now keep in mind that every VPC that you create will, by default, it will come with a default network access control list. That default NACL will allow all ingress and egress traffic across all protocols, all ports, from all sources to all destinations. So again, network access control lists would be our second line of defense after route tables. Once we have routes in place and traffic is flowing, the first stage of filtering that traffic is through network access control lists. Now let's review security groups. Picking up on where we left off earlier, we still have a two-tier application, a load balancer in a public subnet and a application server in a private subnet. Now, the general practice with security groups is that each tier gets its own security group. So our load balancer would get a security group, and then all of the instances that are a part of our application tier would also get their own unique security group. So let's take a look at the security group rules for our load balancer. Very much like we did with network access control lists, we have to open a hole in the firewall to allow the traffic that's needed. So for the security group, we're allowing port 80 and 443 to come in from the internet. You'll notice that we're specifying all zeros for the source. That means any and all IP addresses are allowed to come into the subnet. That means that any and all IP addresses are allowed to enter that security group. Now, For egress rules are a little bit different than NACLs. Here, what I want to draw your attention to is the fact that egress rules apply to initiating new connections. When we think about the nature of our load balancer and how it fits into the architecture of this system, the only connections that our load balancer will ever need to initiate, meaning that there's a brand new connection that's being created, the only new connections it needs to initiate would be on port 8080 to our backend instances. The load balancer should never need to create a new connection to any other host on any other port. And so by specifying this egress rule here, we're saying that the load balancer is allowed to initiate new connections on port 8080, but only to a member of our app security group. So if our load balancer is somehow compromised, it could only send connections to our application server and to nothing else. And so the way that this is enforced here is through security group references. They provide a way to tighten security based on functional tiers. You'll notice that the egress rules of our load balancer is, instead of specifying an IP range, we're specifying the security group ID. In this case, we're matching the security group ID with that of our application tier. So now let's take a look at the security groups for our application servers. Here, they have different ports. The ports that are being used differ than those from our load balancer. So our application server would get its own security group with its own unique set of rules. And here, again, we're using security group references to say that our application server is allowed to receive traffic on port 8080, but only if it originated from our load balancer. No other system within our VPC or out there on the internet is allowed to connect to our application server on port 8080. Only the load balancer can do that. And then, of course, those packets coming from the load balancer on port 8080 can get through the security group and into our instance. And then notice here, because the security groups are stateful, they recognize responses as being responses. We don't need to specify the ephemeral ports in order for them to be returned. They will be returned automatically because the security group recognizes responses as being responses. And so here, again, we only need to specify egress rules in order to control what other system our application server is allowed to initiate new connections to. And so you'll see here that perhaps if we were to keep going and flush out the rest of these tiers, that we would allow our application server to reach our database server on port 3306. So to summarize security groups are applied to instances, be it EC2 instances or RDS instances. They can also be applied to load balancers. They are stateful, meaning that they do recognize responses as being responses. We can specify ingress or egress. We don't have to specify both like we do with network access control lists. Keep in mind that the defaults for a new security group, all ingress traffic will be denied, but all egress traffic will be allowed. So again, security groups are a firewall for our individual devices, be it load balancers, EC2 instances, or database instances, or elastic network interfaces as well. And they provide a way of tightening security based on functional tiers. Now let's review securing the operating system. Now that we've secured our subnets with network access control lists, and we've secured our load balancers and our EC2 instances with security groups, we need to be aware that the security of the operating system is still our responsibility. So as far as the operating system is concerned, AWS is responsible for installing the operating system on that virtual machine. And once that happens, as a customer, we are then responsible for the ongoing security of that operating system. We are responsible for the maintenance of the operating system, access to the operating system, and for installing and configuring any sort of intrusion detection or prevention systems. So the best practices here would be very much like our AWS accounts. We should also follow the principles of least access and least privilege. Not every member of a team needs access to every EC2 instance. And when they do, they don't necessarily need sudo or administrative privileges. We should also look to configuration management services. Within AWS, we have options like OpsWorks. We could also leverage things like Chef or Puppet servers or Ansible Tower so that we can use these kinds of systems to help maintain a known state. So rather than accessing systems on our own and doctoring these EC2 instances individually, doing that, we could end up with a configuration drift where these instances are all in different states. So leveraging configuration management, those third-party tools as well as Systems Manager can help us keep all of our instances in a known and working state. We should also be leveraging change management so that any changes that are made, even if they're made to the operating system, are also recorded. AWS Config can help with that as well. Anything that is done inside that machine should also be logged. We can capture that with CloudWatch logs, and then that provides a trail that can be audited for the sake of satisfying compliance. And then lastly, we should consider immutable architecture. And I would highly encourage you to research that term and how it relates to AWS. There are a number of resources out there that talk about immutable architecture. And the idea there is that once an EC2 instance is launched, it will not change. That the EC2 instance, very much like the world of containers, that once it's running, it will not change. If we need it to change, we go back to either our machine image or the machine image plus bootstrapping scripts or configuration management scripts to ensure that a new machine comes to life in a known and working state, rather than trying to create the state from an existing machine. So remember, again, to recap that all of these things, as far as the operating system is concerned, is the customer's responsibility. Too often we hear of companies having sensitive or private data exposed, and no one wants to be responsible for such an event. Securing our data with both access controls as well as encryption in transit and at rest is of paramount importance. In this lesson, we will review services and practices which can help us do just that. Now let's talk about design principles as they relate to securing our data. The design principle here that we'll focus on through this lesson is that of protecting data at rest and in transit. We should classify our data by sensitivity level. We should use encryption and tokenization where appropriate. We'll discuss those options here coming up. And lastly, we should reduce or eliminate direct human access to the data. Anytime we have the ability for humans to directly access data, it means that that data could potentially be compromised, modified, or deleted or stolen. So by reducing or eliminating direct human access, we can mitigate those kinds of issues. So these are the design principles that we will be keeping in mind as we continue on through the rest of this lesson. Now let's talk about resource policies. Beginning with S3, we have S3 bucket policies. Now these are the same as IAM policies. They're written in the same language, but they're applied at the resource level. Instead of applying these policies to a user, a group, or a role, we apply them directly to the resource. In this case, in this example, we're applying them to an S3 bucket. And now, a number of services support resource policies, such as Amazon Simple Storage Service, Amazon Simple Queue Service, Amazon EC2 Container Registry, and more. Now, with a resource-based policy, we would specify a principal. When you apply a policy to a user, a group, or a role, the principal is implied. It is the entity that we're applying the policy to. But with resource-based policies, because the principal is not implied, we have to explicitly state who that principal is. And that principal could be another account, it could be an IAM user, a group, or a role, or another Amazon service. Or in some cases, it may be appropriate to specify anonymous users in order to make that resource publicly available. And we'll talk about that point a little bit more later on. So here's an example of a bucket policy that is meant to make an S3 bucket publicly readable. You'll notice here that we are specifying an asterisk for the principal. And so we're saying that anyone in the world, even those users who were not authenticated against the AWS API, are allowed to download, that is, call the S3 get object action on anywhere in this particular bucket. Now, here's another example of using a resource-based policy, an S3 bucket policy, to share a bucket with another account. In this case, we are using an AWS account ID as the principal. And so this is saying that this particular account is allowed to upload objects to anywhere in that particular bucket. And because we're sharing it with essentially the root of that account can then delegate that permission to its users or roles or groups. It's worth noting, though, that that other account can only delegate the permissions that we give. And so in this case, we are granting that account the ability to perform the S3 put object action. And so that's the only action that that account can possibly delegate. So remember that with resource-based policies, again, they are written in JSON using the same language as IAM policies, but they are applied to the resource rather than to an IAM entity such as a user, group, or role. And using resource policies, we can enable cross-account or public access to our AWS resources. Now let's talk about Amazon S3 object ownership. Here in this example, we have two accounts. We have an admin account in which we have an S3 bucket, perhaps for the purpose of collecting logs. And we have a development account, specifically for housing development resources. And of course, this is a common pattern within AWS. So the admin account, that particular bucket is essentially owned by the admin account. And we are using a bucket policy to share access to that bucket with our development account. And so that bucket policy is delegating the S3 put object action to the root of the development account. From there, the development account can then delegate further the S3 put object action to our EC2 instances by way of applying a policy to a role and a role to the instance. And so now that we have the policy on the role and we have the role applied to the instance can now upload objects to the S3 bucket in the admin account. But the catch here is that while the bucket is owned by the admin account, the objects are now owned by the development account. The objects are owned by the account who wrote them, not necessarily the account that owns the bucket. And so if we don't do anything more beyond this, if we were to leave it just as it is, then EC2 instances or some other credentials within the admin account would receive an access denied exception when they tried to read those objects from that particular bucket. So the way that we fix that is we can add a condition to that bucket policy. And so the condition here says that the only way that this will be allowed is we're actually going to create a deny action here that says to deny the upload if the XAMZ ACL header is either not set or does not equal bucket owner full control. And so we're forcing, using the bucket policy, we are forcing the development account to upload while setting the ACL headers. And so ACLs apply to the bucket itself. ACLs can also apply to objects, and ACLs provide a very coarse-grained way of controlling permissions. And so you'll see here at the bottom that we have an example of a command line operation that says that we are using the AWS command line tools to use the S3 service running the copy command and setting the ACL parameter to bucket owner full control. And by doing that, that ensures that even though the development account would still technically own the object, the owner of the bucket is now allowed to have full control over those objects. Let's keep in mind that ACLs can be applied either at the time of the put object request or modified later with a separate call. Now let's talk about publicly accessible data. With S3 buckets, for example, there are a number of ways that we can make the data in that bucket publicly readable or publicly accessible in some way. The first way could be to leverage a policy. And as we saw earlier, within a policy, we specify the principal. So within an S3 policy, if we specify an asterisk for the principal, then we are essentially saying that those permissions apply to everyone, even those without an AWS account. The other way could be to apply certain canned ACLs. So ACLs are access control lists that provide a very coarse-grained way of managing authorization for S3 buckets or objects. And so some of the canned ACLs that we need to concern ourselves with here would be public read write, and authenticated read. And so any of these applied to either a bucket or objects in the bucket would cause those objects to be essentially publicly accessible. And so remember that, again, within the shared responsibility model, the configuration and use of these policies or ACLs are the customer's responsibility. It is our responsibility to create and apply the appropriate policy or ACL. It is Amazon's responsibility to faithfully execute against that policy that we configure. Now, I do want to draw your attention here to the authenticated read ACL. It's worth noting because it's counterintuitive. When you first see that authenticated read, you might think, like I did early on, that it applies to users that are authenticated within your account, but that is not the case at all. Authenticated read allows any and all AWS users, including those of other accounts, to access your resources. So I would highly recommend you take the time to understand the various ACLs. Before applying ACLs to a bucket or objects in the bucket, make sure that you know the consequences of doing so. How will those ACLs affect the access to the data in that S3 bucket? Now, another thing we need to keep in mind would be the sharing of snapshots and Amazon machine images. Remember that with EBS volumes, we can take EBS snapshots. With EC2 instances, we can create custom AMIs. And if we can share those things, right? So EBS snapshots can be shared with specific accounts, or they can be made publicly available to all AWS users. And the same thing applies to Amazon machine images. Those can be shared with specific accounts or be made publicly available. And so the things to keep in mind with this is that If you are using AMIs or snapshots that were shared by someone else, that you are doing so at your own risk. AWS will not vouch for the integrity or security of EBS snapshots or Amazon machine images that were shared by third parties. So we always recommended that we get an Amazon machine image from a trusted source. So if you're an Ubuntu user, then look to Canonical. If you're a Red Hat user, look to Red Hat or Microsoft or Amazon Linux. And then remember, if you are the one sharing, whether you're sharing an EBS snapshot or the Amazon machine image, anyone who has access to that has access to all the data that is a part of that snapshot or image. And so if you have created a snapshot that happens to contain sensitive data, then of course you would not want to share that. So be aware of the type of data that is a part of your snapshots and images before sharing them. Now let's talk about authorizing access to private content. There are plenty of use cases out there where you have, some content that is meant to be publicly available, such as website assets, JPEGs, CSS, JavaScript, and so on. These kinds of files you want to be easily served from a publicly readable S3 bucket. And then other content, such as PDFs, EPUBs, MOBI files, digital content, ebooks of some kind, should be kept private and only available to users who are authorized to see it, perhaps users who have purchased those items. And so we have a way of allowing our users to access that private content through CloudFront signed URLs or signed cookies. A signed URL or a signed cookie contains metadata about the object in question, a timestamp, and of course a signature, so that if any of the metadata is tampered with, the signature would then become invalid. And so a signed URL or a signed cookie makes it very, very difficult, if even possible at all, for someone to access that content, some different content, by modifying the actual query. The reason that in this example we're using CloudFront signed URLs as opposed to S3 signed URLs is that CloudFront gives us some more advanced controls over where those requests come from. So one example might be that once we give a user a signed URL, we don't want them posting that URL to Facebook. And so we can limit, through CloudFront, we can limit, say, for example, what IP address that request comes from, so that if the user shares it with someone, the request would be invalid. And so we need to keep S3 private while allowing CloudFront to access S3, and we can do that with the Origin Access Identity. The OAI is a special identity that grants CloudFront the ability to read from our S3 buckets. And then our back-end services running on EC2 or somewhere behind an elastic load balancer, we would dynamically generate that signed URL or signed cookie and return that to our end users. Our end users can then use that URL in order to gain access to that content that they've paid for and have been authorized to access. Now let's review encrypting data at rest. Here we'll talk about the AWS Key Management Service. So the Key Management Service will ultimately stores and manages customer master keys. So in this example, let's think about our application encrypting data. And so our application could make a call to the Key Management Service to request a data key. The Key Management Service will use the customer master key to encrypt that data key. It will then return to us both that plain text data key and the encrypted data key. Our application will then use the plain text data key to encrypt our data. And so now we have both an encrypted data key and encrypted data that is our responsibility to store. KMS only stores the customer master key. And so other systems are responsible for storing the data key and the data. And remember, with encryption, if we lose the key, we lose the data. So KMS only stores and manages the customer master key. And so when we want to decrypt our data, we perform this process in reverse. We would then give KMS the encrypted data key, specifying the appropriate customer master key. KMS will then decrypt the encrypted data key, giving us back a plain text data key that we can use to decrypt our data. So the advantages to KMS is that it is a fully managed, very secure key management infrastructure, right? Managing keys in a very secure way is a hard thing to do. So rather than our team being burdened with that, we can offload that to AWS. Now, it is worth noting that technically speaking, KMS is a multi-tenant software-based service. It is backed and powered by hardware security modules, but the front end, that which we interact with, is software-based and is technically multi-tenant. So there could be regulatory policies that prevent you from using a multi-tenant environment. It does log the use of our keys to CloudTrail so that we know exactly what credentials are being used to refer to customer master keys. And it's also worth noting that the key material, the actual cryptographic material that makes up the customer master key, never leaves KMS. It never actually leaves the hardware security module. We only ever refer to the customer master key by ID. KMS does integrate with a number of other services, and it is compliant and certified to SOC 1, SOC 2, SOC 3, and PCI DSS Level 1. It is within scope for all of those certifications. Now, here's a list of a number of different services that KMS integrates with. If we wanted to perform server-side encryption with S3, then S3 will manage all of the things that we just talked about, that whole process of gathering, data keys and encrypted data keys and storing those. That whole process is managed for us by these other services when they leverage KMS. And so in the case of S3, we will end up with a unique data key per object. In the case of Glacier, it will use a unique data key per archive. For EBS, it will use a data key per volume. For Redshift, it will use what we call a 4-tier envelope encryption. Envelope encryption means that we are using one key to encrypt another key. And so with Redshift, there are actually a number of different keys that are encrypting each other numerous times over. And then with RDS, since RDS builds on top of EBS encryption, we're leveraging the key per volume. So keep in mind that the protection of our data is our responsibility. And within AWS, we have a number of options to choose from in how our data is encrypted, KMS being one of them. And again, KMS, if we are able to use a multi-tenant environment, KMS is an excellent choice for managing encryption keys. Now let's talk about managing SSL certificates. With the AWS Certificate Manager, we can create free SSL certificates, including wildcards. And those certificates automatically renew and automatically deploy. They are backed by Starfield as the root authority, so Amazon would be the intermediate authority in that case. And because of that, they are trusted in all of the major clients. Now, we can import existing certificates, but only the ones that are created by the AWS Certificate Manager will be automatically renewed. But either way, those certificates can be automatically deployed by the Certificate Manager to Elastic Load Balancers, CloudFront distributions, and the API Gateway. So when we look at a diagram of our potential infrastructure, we might have CloudFront edge locations, elastic load balancers. Of course, the certificate manager will automatically deploy those certificates to those devices and automatically renew them. Now, if we need true end-to-end encryption, then of course we would need our connection between our load balancer and our EC2 instance to also be encrypted, in which case we would need an SSL certificate. Now, in that case, since the AWS Certificate Manager cannot reach EC2, as a customer, we would be responsible for installing certificates on the instance. But the Elastic Load Balancer, by default, will accept self-signed certificates. So you don't necessarily have to have a trusted certificate on the EC2 instance. So that makes life a little bit easier if you want to script the EC2 instance on startup to create its own self-signed certificate and install it during bootstrapping. And then by doing that, your connection will be automatically encrypted between the load balancer and the instance. It is possible to set a policy on the load balancer that instructs the load balancer to only accept certain keys. So you can add a public key type of a policy to the load balancer, and that will then authenticate the backend instance with that given public key. Now, it's also worth noting that CloudFront does not accept self-signed certificates from an origin. And so if we place an Elastic Load Balancer as an origin behind a CloudFront distribution, we must use a trusted certificate. Now, I've seen this happen in the past where HTTP connections to my CloudFront distribution were working perfectly, but HTTPS connections were not, and I couldn't figure out why that was. I spent a long time trying to debug that, and then when I finally discovered in the documentation, the edge location required a trusted certificate. And once I resolved that trusted certificate, then everything worked just fine. So keep that in mind. Right, so keep in mind that in terms of security, encrypting our data in transit is a vital step in the overall picture of a secure environment. And with the AWS Certificate Manager, that gives us a very powerful option for ensuring that our SSL certificates that are used by CloudFront, load balancers, and the API gateway remain up to date, and that our traffic remains trusted and secure throughout its journey from end to end. Now let's talk about encrypting database connections. So we've already reviewed how we can ensure encryption of web or API traffic using SSL certificates. But true end-to-end encryption would also mean that the connections between our EC2 instances and our database would also be encrypted. And so it's important to understand that when we're using RDS, this would also apply to running it on, on EC2 yourself. But at least with RDS, each DB engine has its own process for implementing SSL. So, Postgres, Oracle, SQL Server, MySQL, Mariah, and so on will each do things slightly differently. So we'll need to keep that in mind and read the documentation on a per engine basis. Now, you may need an intermediate certificate in order for your application to trust the certificate coming from the RDS instance. And so in that regard, each region offers its own intermediate certificate. And of course, you can find those endpoints where to download that certificate from the AWS documentation. Now, for most database engines, now some might be different than others, but generally speaking, RDS, at the time you create the DB instance, RDS will create and install the SSL certificate on that instance for you using the instance endpoint, the DNS endpoint, as the common name. And so from there, then it would be our responsibility to ensure that our application is indeed using an SSL encrypted connection. And of course, whatever user we use to connect to the RDS instance, we could use grants or alter users or alter tables to enforce SSL connections for that particular user. And so again, between SSL certificates on our load balancers and CloudFront distributions and SSL certificates on our databases, we can achieve true end-to-end encryption, ensuring that our data is indeed encrypted in transit. Based on the cost optimization pillar of the well-architected framework, this module will review pricing models, cost contributors, and various strategies we can use to optimize for cost when designing and running systems within AWS. Cost savings is perhaps one of the primary drivers of AWS adoption. But in order to realize those cost savings, we need to be fully aware of not just the dollar amounts we pay, but the things we pay for, those options and fine details that actually contribute to costs. In this lesson, we review the cost models and highlight often overlooked cost contributors for various services. Now let's talk about design principles as they relate to cost optimization. When it comes to cost optimization, there are a number of design principles that we can pull from the well-architected framework that can help guide our decisions. The first is to adopt a consumption model. That means that within AWS, within the cloud, because of the on-demand nature of resources and the pay-as-you-go pricing, it means that you pay for what you use, but use what you need. And so it takes some forethought and some ongoing monitoring and constant reevaluation of our choices to ensure that we are using what we really need rather than being over-provisioned and paying for more than we need. Next would be to measure overall efficiency. We want to take the time to, again, monitor what we're doing, monitor what we're, the business output, and monitor our cost so that we can understand the gains by increasing output and reducing costs. Next, we have stop paying for data centers. As we know, data centers are an enormous capital expense and, of course, regular ongoing fixed expenses as well. And so with AWS, because AWS in the least is responsible for the physical infrastructure, and in many cases we can also have them be responsible for the platforms and software as well, then we can have plenty of opportunities within our own applications and infrastructures to offload the operational burdens to AWS, which then lowers our total cost of ownership. We also have the principle that says that we should analyze and attribute costs. And so we have a number of mechanisms within AWS, such as tags in multiple accounts, AWS organizations, that can make cost attribution much easier and much more transparent so that we know exactly, down to the penny, how much a particular project, environment, cost center, team, or so on is actually, costing within AWS. And lastly, we have reduced costs with managed services. And so here, like we talked about earlier, we have the ability now to shift responsibility, the operational burdens, not just for the physical infrastructure, but also for common services that don't necessarily add, differentiated value to our application. Right? So when you think about things like RDS for databases and allowing Amazon to handle, the burdens of managing a database or a queue or a NoSQL database or video transcoding, the list goes on. In all of those cases, we could potentially lower our costs per transaction or per service by leveraging these managed services since they operate at such a vast scale, what we would call cloud scale. So these are the design principles that we will keep in mind as we move forward throughout the rest of this lesson. Now let's talk about right sizing. Now, when we think about running applications on EC2, we need to consider a number of things, such as what size instance does our application really need? We talked about this very point earlier on when we talked about performance, but the same question applies to cost. Not every application needs to run on an M4 16 extra large, right? The cost of such a machine is not often warranted. We should also ask ourselves, what size EBS volume does our application really need? Not every application needs a 16 terabyte volume. And then the same would be true for IOPS. What level of IOPS does our application really need? And the only way to answer those questions, as we talked about earlier, is through monitoring. So monitoring the performance of our applications, monitoring the performance of our volumes, our EC2 instances, can inform our decisions even while cost may drive those decisions. Now, we should also think about right-sizing our fleet. So not just the individual instances, but how many instances do we need? Auto-scaling helps match supply with demand, thereby avoiding over-provisioning. We're no longer, within AWS, we are no longer provisioning for peak. We are provisioning for the current demand, and we know that through monitoring. So just like we talked about in reliability and performance, we can leverage monitoring to inform us as to what the current level of demand is, and then auto-scaling helps match the current supply to that demand so that we can avoid over-provisioning. Over-provisioning means that we're wasting money. Now, these same questions would apply to RDS, right? What size RDS instance does our app really need according to the data model, the amount of data, the amount of queries, reads and writes, and so on. Now, we should also ask, are provisioned IOPS really necessary? Keep in mind that this is true for EBS as well, that some applications may not actually need provisioned IOPS. It all depends on what's actually going on, the patterns of data access, and of course monitoring will show us that. Perhaps you would be perfectly served, or this application would be served well enough with a general purpose volume. So remember that with EBS volumes, we would pay for the storage and any provisioned IOPS we request as well. So we can lower our costs by reducing or eliminating provisioned IOPS where possible. Another thing to consider would be, could we run several different databases on a single instance? It may not be necessary to run an individual database on an individual instance and thereby paying, for a number of instances. Some cases you may very well be able to combine numerous databases on one instance and save money that way. Right? So in terms of EC2, in terms of RDS, and really everything, these kinds of thought patterns and decisions and questions would also apply to Lambda. How much memory do we need? What's the execution timeout? So these kinds of questions we should be asking ourselves so that we ensure that everything we do in our environment is optimized for cost. Now let's take a moment to understand the costs of Amazon S3. When we have an infrastructure that's leveraging S3, this is true for any component within our infrastructure, we need to take the time to understand and be aware of not just the dollar amounts that we pay, but the things that we pay for, those things that actually contribute to cost. So with Amazon S3, first, we need to understand that for the different types of requests, we are charged per 1,000 requests. So when we're making millions and millions of requests to S3, that will, of course, contribute to our bill. Now, GET requests will have one fee, put, copy, post, and list requests will have another fee. But either way, they all contribute to the overall cost of S3. So that's an important thing to consider, is the cost of S3 is not just, storage per month. It's also related to the number of requests that we make to that bucket. So in that regard, one of the things that we can do in our code, and this is where DevOps culture comes into play, someone who is very familiar with, the inner workings of AWS can work with developers writing code against S3 to help understand, how our decisions in code will affect our bill. So one example here would be that, in our code, instead of checking for the presence of the bucket before reading or writing, we simply handle any exceptions that might be returned, right? So if you think about that for a second, if every time we read or write to a bucket, we have to first check to see if the bucket exists, that's a request. And so by removing that request, we can cut the number of total requests in half. And that would reduce our bill for S3. Keep in mind that as far as storage goes, for data that we don't need to access, for data that we need to keep but we may never actually look at, we can use lifecycle rules to transition that data to Glacier and then reduce our costs very significantly by transitioning that on to long-term storage. Another thing to keep in mind is that in terms of bandwidth, inbound bandwidth is free. So if we go back to some of our earlier examples where our end users were uploading directly to S3, that inbound bandwidth would be free. Outbound bandwidth, though, is a different story. Bandwidth between S3 and EC2 in the same region is free, but bandwidth from S3 to the internet or to another region will have a certain fee per gigabyte of bandwidth. So again, it's important for us to keep in mind all of the things that contribute to the cost of a particular service. In this example, we talked about S3, but the idea applies to every service. Some services like S3, the costs are more than just the storage, or more than just what it might seem like on the surface. So in terms of cost optimizations, we really need to take the time to be aware of all of the things that actually contribute to cost, and then analyze how our decisions during implementation of that service are contributing to our overall bill. Now let's take a moment to understand the costs of Amazon VPC. When we're deploying any particular architecture that leverages Amazon VPC, there are a number of things we need to consider. So for most managed devices, such as the Elastic Load Balancer, the NAT Gateway, VPN connections, Direct Connect, those will have both an hourly charge and bandwidth charges. So keep that in mind, that the costs are not simply, the hourly fees, but also based on the bandwidth that passes through them. Now, some other things to consider would be network address translation. Do we run it on a NAT gateway, or do we run it on an EC2 instance? So we need to consider that the NAT gateway is capable of 45 gigabits per second, and it's fully managed. It's already inherently fault tolerant, horizontally scaled, redundant, all of those good things, right? So yes, an EC2 instance can provide network address translation, but we need to consider that if we were to try to match the capabilities of the NAT gateway by doing it ourselves on EC2, we should keep in mind that the next closest instance is the M416 extra large, capable of 25 gigabits per second. Depending on the region we're in, that machine could be upwards of 70 times more expensive. And we should consider that the 25 gigabits worth of bandwidth is only possible, that kind of throughput is only possible within a particular availability zone. It's not possible between an instance and the internet gateway. So the NAT gateway, will be cheaper and outperform an EC2 instance. With that in mind, we can conclude that the fully managed NAT gateway will generally be the cheaper option for performing a network address translation. Some other things to consider would be the fact that for many architectures, we may very well leverage cross-AZ traffic. We may have different instances in different availability zones for the sake of high availability and fault tolerance, for the sake of being resilient to the loss of a data center, but we need to remember that traffic crossing the availability zones does incur a cost, and the cost is per gigabyte worth of bandwidth. The same is true for VPC peering. So any traffic crossing a VPC peering connection will also incur bandwidth charges. Now, a VPC peering connection, the thing to keep in mind about that as well is that even if the two instances that are communicating are in different VPCs, even if they're in the same availability zone, the fact that they're communicating across a VPC peering connection means that they would still incur that cost. So when we're leveraging Amazon VPC, and like we talked about with S3, for any service that we use within AWS, we need to take the time to be aware of the fine details of that service and how that affects our costs. I've heard firsthand accounts from numerous consultants and enterprises that I've worked with on how these kinds of things has come back to surprise them with much larger bills than they expected. And so in that regard, they had to re-architect and re-implement things in order to save money by, in some cases, foregoing resilience to the loss of an availability zone so that they could remove the cost of cross-AZ traffic, right? So again, when it comes to cost, let's be aware of all of the things that contribute to the overall cost. Now let's talk about cost savings with temporary environments. When it comes to cost and controlling costs within AWS, for any given infrastructure or for any environment, why pay for an environment that's not being used? So instead, we can turn out the lights. We can clean up after ourselves, right? We can build an environment when it's needed, tear that environment down when it's not needed, and only pay for the time that that environment actually ran. One strategy here is when we think about certain environments like development environments may not actually even be used at nights, on weekends, on holidays. We may have testing environments that are only used for a short period of time to perform a test and then not needed for some time later. So we can leverage things like CloudFormation. In this example, we have a CloudFormation template that's stored in code commit. We have a CloudWatch events rule, a time-based rule that triggers code commit at a regular interval, say every morning at a particular time or every Friday at a particular time, whatever the case may be. So on that schedule, the CloudWatch events rule can fire, triggering code pipeline to automatically pull that template from code commit, pass it to CloudFormation, and allowing CloudFormation to automatically build out that environment, all of the components necessary for that environment. And then, of course, we pay for those components for the time that they exist. We perform our work, we perform our tests, and then when we no longer need it, we can simply go to CloudFormation and delete that stack, thereby deleting the resources and saving that money. So keep that in mind, that temporary environments and the ability to have systems like CloudFormation, Code Pipeline, and CloudWatch events, build them automatically when they're needed, is a very powerful pattern for helping to control costs within our AWS account. Now let's talk about billing alarms. No discussion about cost within AWS would be complete without talking about billing alarms. Billing alarms are one of the most crucial things that you can do to ensure not only a cost-effective environment, but also a secure environment. Billing alarms can help you be aware of rising costs for any number of reasons. It could be that costs are rising because of a runaway script, because someone made a poor decision, or because your account credentials were compromised, right? So when we look at this diagram and we see that the point of this diagram is just to say that we have potentially a lot of moving parts. We have load balancers, we have auto-scaling groups of EC2 instances, we have RDS running in a multi-AZ deployment, meaning that we have 2 instances. We have CloudFront distributions in multiple S3 buckets that are storing things. We have perhaps DynamoDB tables, Kinesis streams, Redshift clusters. We might have Amazon EMR clusters. We might be using Athena. We might have a number of different Lambda functions and queues and simple notification service topics. The list goes on. In any given infrastructure, we could have a lot of different moving parts that are all contributing to our cost. And then, of course, we might duplicate this very thing into another region, thereby doubling our cost. Anything that we add to our infrastructure will increase our cost by some amount, and the things that we remove will decrease our cost. And it is possible, and I've read these firsthand accounts and spoken with people over the years that have seen very significant shifts in their costs, either for the better or the worse, simply by making what appeared to be one small change. And so we can help keep ourselves aware of changes in cost by leveraging billing alarms. So we can monitor our estimated charges with Amazon CloudWatch. Amazon CloudWatch collects billing metrics several times every day. Now, the collection of those billing metrics actually happens in the U.S. East Northern Virginia region. And so as a result, the billing alarms have to be created in that region, right? Now, the alarm triggers when the actual billing exceeds the threshold that we set. AWS does not use, for the sake of billing alarms, AWS does not use any kind of forecasting or prediction for that billing alarm. It's an actual value. So when your billing alarm actually triggers, you know that you have already spent that amount of money. So what I typically suggest is, use the monitoring to, when you're brand new to AWS, you don't really know what your spend might be. So use the monitoring to measure what your spend is over some period of time and find that baseline of typical behavior and then set a billing alarm to that or slightly higher. So let's say, for example, our typical monthly spend is somewhere around $12,000. So I would set a billing alarm for, say, $12,500, maybe $13,000. And if I saw that if the alarm didn't go off at all, then everything is probably fine. If the alarm goes off in the last week, very close to the end of the billing cycle, then everything is still probably fine, but we might want to look to see, investigate costs to see if anything was maybe off. If the alarm goes off halfway through or before, if the alarm goes off closer to the beginning of the billing cycle, then something's going on. That would definitely indicate that there was a very significant change to your environment. And at that point, you would probably want to take some time to make sure that you knew, what that was, whether it was intentional or a runaway script or perhaps something nefarious happening with compromised credentials, right? So billing alarms, again, are one of the most crucial things that you can do to help maintain a cost-effective and secure environment. Based on the operational excellence pillar of the well-architected framework, this module will review the principles that guide our business and engineering teams to most effectively leverage the tools and techniques we've discussed so far. Keep in mind that while cost savings is indeed a major driver in AWS adoption, the number one driver is the increased agility and flexibility organizations can achieve compared with traditional IT. But in order to truly realize those benefits, we need to approach our implementation of AWS in a particular way. In this lesson, we will discuss a number of principles and techniques, as well as some of my personal experiences and how they embody the premise and practices of operational excellence. Now let's talk about infrastructure as code. If you remember, one of our first design principles is that operations should be performed as code. And so when we think about the benefits of the cloud, performing operations as code is really the only way to realize those benefits. So we have a number of benefits, including a level of agility and flexibility that we never had with a traditional on-premises IT. We have the ability to achieve much lower times to market. We have a much greater capacity for saving money with the cloud than we did with on-premises. We have the ability to perform fast and efficient deployments. We can create environments that are self-healing and scalable. And then, of course, we also have the ability to create environments that are highly secure. You know, giving us we have the tools that can provide real-time monitoring of everything throughout our entire infrastructure. And so the only way to truly realize all of these benefits is through automation. Manual processes simply cannot allow us to realize these things. And so we have a lot of tools available to us for automation. Within AWS, we have a number of tools. We have the CLI tools, we have the software development kits, and of course we have AWS CloudFormation, which we'll talk about here in just a moment. We have AWS Elastic Beanstalk, we have AWS OpsWorks, and then we have plenty of third-party tools such as Troposphere, Terraform, Ansible, and of course SaltStack. And so the idea here is that, you know, we're not saying that any one of these tools is better than the others. We're not saying that anything here, your choices here are necessarily right or wrong or better or worse. We're saying choose one. That automation is key regardless of the actual tools that you use. It's better to automate than to rely on manual processes. So now let's take a look at a diagram and talk about the workflow when using something like CloudFormation. So with CloudFormation, we can describe or define our resources as templates, and we can write that in either YAML or JSON. I'm a huge fan of YAML because it's less syntax heavy, it's easier to read, easier to write, and it supports comments, which are really useful for ongoing maintenance. So keep in mind that comments are not necessarily for yourself. Comments are for the person coming behind you, explaining to them why you're doing what you're doing, what this particular pattern is trying to achieve, or in the least, reminding yourself of why you did what you did 6 months later. And then, of course, we can take that template. It is code. We should store that in a version control so that we can collaborate with other members of our team. And of course, within AWS, we have Code Commit that provides private Git repositories perfect for storing our templates. Now, of course, we could use GitHub or Bitbucket or something else, but I really like that Code Commit natively integrates with a number of other AWS services, and that the authorization controls are already built into IAM. From there, Code Pipeline can respond to a code push. So our developers write the template, they commit locally, push to Code Commit, and then that could trigger Code Pipeline to then automatically pull that template from the repository and then deploy that on to CloudFormation through various stages of a continuous integration and deployment pipeline. From there, we could have Code Build or Lambda programmatically validate templates and test the environments after they're built. So before the template is even built by CloudFormation, we can use Code Build or Lambda to validate that template against known business policy, security standards, compliance needs, and so on. So rather than allowing something to be built that we know won't work, we can already prevent those kinds of things by looking at the template, because the template will describe the exact nature of that environment. And then, of course, once that template is actually built by CloudFormation, we can, again, use code build or Lambda to run functional or test or performance tests, load tests, whatever the case may be, on an existing infrastructure. And we can deploy these infrastructures as parallel environments into, say, a dev, a test, or a staging environment before making those changes to production. And of course, once those validation tests pass, we can then pass it on to CloudFormation that actually builds the resources that we've defined in our templates. Once that has finished, we can then manage that collection of resources as a stack. And that collection of resources, that environment, may very well be temporary. It could be built just for the sake of running some performance tests. We gather our data, and then we throw that environment away. And we can do that very easily simply by deleting the stack. Or we leave it, and then we continue to iterate by making changes to our template and pushing it back through the process. Now, Cloud Pipeline and CloudFormation can both send notifications along the way during various stages and events. As different things are happening throughout the life cycle of this pipeline, we can subscribe to those notifications and have them delivered and integrated into our existing workflow and services, such as collaboration tools, so that our engineers, our developers, they don't necessarily have to leave an environment that they're already in. They don't have to go looking for information. The information is given to them in a tool that they're regularly looking at and helping them to stay informed as to the current status of an automated process. So again, automation is absolutely key. It's the only way that we can truly realize all of the benefits that AWS has to offer. Now let's review the evolutionary process of operational excellence. When we think about our approach to AWS, we have workloads that need to be deployed, they need to be designed, they need to be coded, deployed, and all of the things that go along with that. We could summarize by saying that we first start by designing a system that will run on AWS. And of course, that requires education. We have to educate ourselves, educate our team, so that we are aware of our options and what it means to choose one particular infrastructure over another. We then code those decisions. We express that infrastructure through code so that we have a much easier ability of making changes later. As we've talked about with automation, that gives rise to a much more efficient, reliable, and secure environment. Once we've coded that, we can then deploy that with automated processes. And once it's deployed, we can then test that infrastructure. And those results will then feed back into the design for the next evolution. And as we are iterating on this infrastructure, on our applications within AWS, we are also considering ongoing monitoring. So the ongoing monitoring of our infrastructures are also continuously, regularly influencing our design decisions for the next iteration. We're also considering new technologies, new features, new services. We're considering failures and the lessons learned from those failures. So everything we do within AWS is an evolutionary process. We're constantly evaluating our decisions and looking for ways to improve. And if you think about this, this is the way that it's been for decades. We've always followed this process. The real revolution here is that when you compare the cloud with traditional on-premises, I think the greatest difference is the time between iterations. When I was teaching a lot of live classes in person and traveling all over the country to Fortune 500s teaching AWS topics, I would often ask, How do you measure time between deployments? And so often I would hear, weeks or months, sometimes years, right? So that's a very long time between iterations. But within the cloud, we can reduce those months or weeks or sometimes years down to hours. So imagine being able to iterate on an idea or a prototype several times in one day. That is the power of AWS. And the only way to achieve that is through automation. And so this is what drives our adoption of AWS. This is the lens that we should be seeing things through, is that we're designing, we're coding, we're deploying, testing, validating, and then feeding those decisions back into the loop so that we are iterating and always looking for ways to improve on reliability, on performance, on security, on cost effectiveness, and that will give us an operationally excellent infrastructure. Now let's review a case study of running Cassandra on Amazon EC2. A couple of years ago, I had an opportunity, a really amazing opportunity, to work for an organization in a completely greenfield environment. It was a brand new AWS infrastructure, and the development team had already decided that they wanted to use Cassandra. And so, even initially I tried to argue for DynamoDB, but they had already written code, they already had working prototypes, and we just needed to move forward. And so we decided to, all right, let's build Cassandra. And the way that the lead engineer wanted Cassandra built was to leverage 6 nodes so that we could have a 3-way replication. So the way that we went about this, we took our time. Part of operational excellence says that we understand our workload, we take the time to understand the technology, the options that are available to us, and design something in order to implement. And it doesn't mean that we have to be perfect the first time. It means that we take our time and do our best, we get it out there, we go to market, we monitor it, and then we evolve. Now, of course, at the time, I didn't have the phrase operational excellence. We didn't really think that we were operating this way. But in hindsight, it's clear that our team was adhering to most, if not all, of the principles of operational excellence. And that's what I'm hoping to illustrate here with this example, this case study. So our first iteration of Cassandra on EC2, we chose an M3 large, primarily because we thought that it gave us the right blend of CPU and memory, and more importantly, that it gave us a 32 gig SSD volume, which was an instant store volume, right? So it also had, somewhere around 2 cores and about 8 gigs worth of memory. But again, the most important factor for us was that 32 gig SSD volume. At the time, we thought that we really needed the IOPS that were capable, that were provided by an instance-based store. So what we were working with was the fact that instant store volumes are ephemeral. When the instance terminates, the data terminates or gets deleted. And so we achieved durability through 3-way replication. So we had a 6-node cluster with 3-way replication. We had Cassandra configured to be aware of AWS regions and availability zones. So that meant that we could lose 2 availability zones and still have a copy of the data available. We achieved high availability through multiple auto-scaling groups. We had an auto-scaling group for seed nodes and another auto-scaling group for non-seed nodes. So the thing with Cassandra is that all nodes are equal members of the cluster, except that seed nodes actually contribute to quorum. They help elect leaders and help maintain the state of the cluster. And so we wanted to separate those into different auto-scaling groups. That just made the automation process a bit easier when it came to distinguishing a seed node from a non-seed node. But either way, each member of the cluster actually held and served data, regardless of whether it was a seed or non-seed. We also leveraged a custom Amazon machine image that Cassandra was pre-installed on and ready to go. That way, when new machines booted and joined the cluster, we didn't have to wait for Cassandra to be installed or compiled. It was already there, ready to go. And if we ever wanted to update to a later version of Cassandra, we would go back and rebuild a new AMI. Now, as far as the configuration of Cassandra and the management of the Cassandra daemon process, we handled that through Ansible playbooks. So that particular process, the steps it took in order to get Cassandra configured and started and ensure that a new node could join the cluster, that was fairly involved. There were a lot of steps that needed to happen in a very particular order, in a very particular way. And the only way to really manage that was through automation with something like Ansible. There was no way for us to really rely on doing that manually. It was too involved, it would have been too slow and too unreliable to count on a human doing that. We also leveraged a number of tags, partly for keeping our environment organized, and those tags also leveraged automation. Our automated processes within Ansible and other things, as we'll talk about more here in just a little bit, looked to those tags in order to help understand, what cluster, what environment, in what type of node this new server is supposed to be. And so this first iteration of this Cassandra cluster ran really well. We ran 3 of these across different environments, and for the most part, it ran perfectly fine. It was very stable, but when we had issues, they were significant issues. We never seemed to have small issues with Cassandra on EC2. In our particular case, we always seemed to have very significant things that required a lot of time from cloud operations team in order to get it back up and running, ensuring that we didn't lose data or in some way adversely affect production. Now, we also leveraged, in addition to CloudWatch, we also leveraged Datadog to provide active real-time monitoring of the Cassandra process. We wanted to be aware, we wanted to be alerted, informed in real time if the Cassandra process actually failed and stopped reporting to monitoring service. Now, the reason we used Datadog versus something else was that, yes, CloudWatch gave us system-level metrics and it gave us a number of useful alarms. Datadog provided a more in-depth view of the actual Cassandra process, information pulled from the JVM, leveraging JMX monitoring. Of course, we were also using New Relic for other applications, but Datadog at that time had a much more mature integration with Cassandra than other monitoring services. This cluster ran perfectly fine for a number of months, but when it had issues, they were significant issues. In our experience running Cassandra, we never really seemed to have small things. All of our issues were fairly significant, taking a lot of time from the cloud operations team, which meant that we were then unavailable to help development with new features and new services that they needed to be built within AWS. And so we're going to come back to that point here in a little bit. One of the issues that we had with Cassandra was that our DBA, in his management of the cluster, determined that we needed to run compactions. Compactions are a way of helping to optimize disk use. And we found that our disk use was growing a bit faster than we thought it would. Again, we only had 32 gigs. And so the particular compaction strategy that our DBA used, ironically, needed twice the amount of disk space that we had. The end result of compaction is, ideally more optimized disk usage. But the process of compaction, at least for that particular strategy, required more disk space than we had. And so we ended up seeing these I/O exceptions, no space left on device. And so the first instance we ran this on essentially ran out of disk space. And it meant that we couldn't actually complete the compaction, which meant that that instance was left in an unusable state. And so now we had this issue where we knew we had to redesign, re-architect, and re-implement a new version of a cluster. We had to address these issues. And so we didn't want to rush and hurry. We wanted to take our time to really try to understand more about Cassandra and more about how we could truly improve this in the long run. And so as a temporary stopgap measure, what we did was that one machine, we simply rolled it over. We terminated it and allowed our automated processes to bring up a new node. And then as a temporary step, in order to hold us over and prevent disk space issues until we could redesign, what we did was we added to each member of the cluster, we added a 100 gig EBS volume. We stopped the Cassandra process. We mounted that EBS volume. We did an rsync from the instance store volume to the EBS volume. We then remounted the EBS volume on top of where the instance volume used to be, and then restarted Cassandra. And now Cassandra still had the exact same data in the exact same place, but now it had 3 times the amount of disk space available to it. And that gave us time to redesign and architect and implement a new version of this cluster. And that new version looked something like this. Our new version, after considering the different technologies that were available, we felt like the M series was still a good choice because it gave us the right blend of CPU and memory. But we realized that we didn't actually need the high IOPS performance with ephemeral instance-based stores. That EBS volume served just fine. And so we put all of this in place, and then by leveraging autoscaling, all we had to do for each member of the cluster in order to roll each member over, we simply used the CLI tools. And this was the only manual step in the entire process. This one manual step kicked off an entire chain of automated processes. And this step was to tell autoscaling that that particular node was unhealthy. And as a result, autoscaling would then terminate that instance and then replace it with a new instance, including an EBS volume. And so the new version, this new launch config, would launch an M4 large with a 400 gig SSD general purpose volume. In our research of monitoring, we discovered that we really didn't have near the IOPS that we thought we would. This particular cluster just didn't really need a lot of IOPS. So we found that the general purpose SSD operating at 3 IOPS per gig, in this case a 400 gig SSD volume, gave us 1200 IOPS, which was perfectly fine for this particular implementation of Cassandra in our workload. From there, once autoscaling created that new instance, it would then automatically apply a number of tags, again, in order to inform the rest of the automated processes, which cluster this machine should belong to, what type it is, whether it's a data node or a seed node, what environment. And then what I want to draw your attention to here is the fact that we added an additional tag that said bootstrapping equals pending. So the tag was set initially to a pending status so that we can look for that tag to have a different value later. From there, autoscaling, leveraging autoscaling lifecycle hooks, we could subscribe Lambda to those lifecycle hooks, and then autoscaling would then trigger Lambda functions. We specifically looked to the new instance launching lifecycle hook, and then once Lambda was triggered, the Lambda function would leverage the Amazon EC2 API to call the describe instances action in order to retrieve metadata about that new instance. Lambda would then take that metadata and trigger Ansible Tower. Using the Ansible Tower API, it would feed that metadata to Ansible Tower. Ansible Tower would then shell into that new instance and bootstrap the Cassandra daemon, creating the necessary configuration files, starting the Cassandra process, and then ensuring that everything was in place in order for that particular node to join the cluster. Throughout that process, our team could log into the Ansible tower and look at a real-time dashboard and see all of the steps that were taking place, from Ansible running the playbook on that node. And we could watch and see if anything failed, we could then step in and take manual action. But for the most part, all we had to do was sit back and watch. And then once Ansible Tower was finished, once that playbook had completed all of its steps, the last thing it would do was set that bootstrapping tag from pending to complete. And then we would know that all of the automation process was finished. Now, we were also leveraging Datadog in combination with CloudTrail and CloudWatch. So Datadog was pulling in metrics from CloudWatch. It was pulling in CloudTrail logs so that we could then see a real-time health dashboard so that we can monitor the health of this cluster and the individual nodes within it in real time simply by glancing at the dashboard. And so once a new member joined the cluster, we could then look to Datadog. Once we saw that bootstrapping was complete, we could then look to Datadog to ensure that, yes, indeed, we do see that new member having joined the cluster, and the old member is now gone. And then we also leveraged PagerDuty to provide incident response to our team of on-call cloud operations engineers. And so with PagerDuty, it would first send a text message, a push notification. If we didn't respond, it would start making phone calls. If we didn't answer, it would then escalate to the next person. Combining all of these tools, we created a very automated, very powerful way of managing clustered services in AWS. Now from here, again, like I mentioned earlier, Cassandra was fairly stable, but when we had issues, they were significant issues. After a lot of discussion with the development teams, we finally stopped what we were doing and we took some time to analyze our use of Cassandra. We looked at how much data we were storing, the number of records we had, the nature of our queries, how much are we reading, how much are we writing per second, and we really took a lot of time to gather as much information about our usage of Cassandra as possible in order to compare how that same usage might look on DynamoDB. And what we discovered was that this particular Cassandra cluster cost us about $900 a month, which in the world of enterprise services is not really a lot of money. But when we compared that same usage to DynamoDB, we predicted that we could cut our costs from $900 a month per cluster to $60 a month using DynamoDB. And from there, we went on to work with the development team to re-architect their software to use Dynamo rather than Cassandra. And so, again, what we've been talking about here in this case study is trying to illustrate the principles of operational excellence. We took our time to understand the workload, to understand the technology. We designed something, we implemented it, we monitored, and then we had mistakes, we learned from those mistakes, and everything we did fed back into another iteration and another evolution of our, not only the implementation details, but also our processes, also the way that we went about managing these services. So that is our case study of Cassandra on Amazon EC2. Throughout this course, we've covered a lot of information relevant to the AWS Solutions Architect Associate Certification. We've talked about reliability, resilience, and performance of our networks, computing, and storage. We've discussed cost optimizations, tools and principles for creating secure environments, and principles and services that enable operational excellence. I would highly encourage you to watch this series of videos again, as you will likely get more out of it the second time. I would also encourage you to study each of the services we've covered here and research other use cases as a way to help further ingrain this knowledge. Remember that nothing beats hands-on experience. Practice some of the basic labs available on the AWS website. Begin to gain experience by designing solutions to existing problems, or perhaps by redesigning a technical challenge you've had in the past. Review these designs with colleagues who are already certified, and most importantly, implement these designs yourself. Remember that our decisions in AWS are not fixed. Any environment can be temporary, so practicing shouldn't cost much money at all. Play with the technologies offered by AWS and have fun building and discovering. And lastly, thank you for spending this time with me and allowing me to share this knowledge. I'm genuinely excited for you to become part of the greatest IT revolution of our lifetimes and achieve your AWS Solutions Architect Associate certification. And keep in mind that when I'm not teaching or recording, I'm consulting. If you would like to engage with me in some way, to offer feedback on this material, to suggest topics you would like me to cover, or even just to tell me you passed the exam, I would love to hear from you. You can reach me via email, videos@cerulean.systems. I wish you good luck on the exam and the very best in all that you do with Amazon Web Services.